On the 9th of October 2022, a little after 1 o'clock in the afternoon, Universal Time, most of the gamma-ray detectors in orbit around the Earth stopped working properly. Nothing was damaged, they were simply overwhelmed, in the way a microphone is overwhelmed by a sound too loud for it to record. The instruments aboard Fermi and Swift, and aboard half a dozen other spacecraft, are built to count individual particles of the most energetic light there is, one at a time and very precisely. For several minutes that afternoon, they could not count fast enough to keep up. Somewhere in the constellation Sagitta, a small and faint arrangement of stars that almost nobody has ever learned to find, something had happened. The light from it had been traveling for 1.9 billion years before it reached the outer edge of our atmosphere. When the measurements were finally pieced back together from the instruments that had come through the encounter intact, the burst turned out to be about 70 times brighter than anything of its kind ever recorded. Something else happened that afternoon, much closer to home. Radio operators monitoring very low-frequency signals across the daylight side of the planet picked up a disturbance in the upper atmosphere, in the layer of thin, electrically charged air that sits 60 to 100 kilometers above the ground. Our own sun stirs that layer regularly, and nobody finds it remarkable because the sun is 8 light minutes away. This had been traveling for 1.9 billion years and still had enough left in it to do the same thing. For a few seconds, and it is only ever seconds, a single point in the sky becomes the brightest object in the universe. Not the brightest star in a neighborhood of stars, and not the brightest galaxy in a crowd of galaxies. For that handful of seconds, it outshines the entire galaxy it belongs to, every star in it at once, by a factor running well into the millions. And it does all of this in a kind of light your eyes cannot register at all, which is probably for the best, since anything close enough to watch it properly would not survive to describe it. The light itself is worth pausing on, because it is not light in any ordinary sense. Visible light, the narrow band the human eye evolved to catch, carries roughly enough energy to nudge one electron in one molecule at the back of the retina. A gamma ray carries millions of times more. It does not so much illuminate matter as pass straight through it, and where it fails to pass through, it breaks something on the way. The quantity of energy involved is hard to take hold of, so it is worth going slowly. Our sun has been burning for 4.5 billion years, and it has something like 5 billion left. Across that whole span, it will release a finite amount of energy, a very large number, but a fixed one with an end to it. The burst that arrived in October of 2022 released, in the one direction that happened to include the Earth, roughly 10,000 times that entire figure. 10 billion years of sunlight multiplied by 10,000 delivered in about 5 minutes. They are not rare either. Several hundred are picked up every year, which works out at something close to 1 a day. They have been arriving at that rate for as long as anyone has been able to notice, and for billions of years before that. As you are listening to this, the odds are decent that one is on its way, or has just finished arriving. It will have come from a galaxy nobody has ever bothered to name, because there are hundreds of billions of them, and nothing like enough people for the work. Every one of them is something ending. Most are a massive star that has finally exhausted the fuel holding it up, collapsing inward under its own weight in less time than it takes to draw a breath. Some are 2 dead stars, collapsed long ago and dense beyond any useful comparison, that have spent hundreds of millions of years spiraling toward one another and have finally run out of distance. None of that was understood for a very long time. The first of these was recorded in 1967 by machines that were not looking for it and by people who were not allowed to say so. It took 30 years after that to work out how far away they were, and another 20 to be reasonably certain what was causing them. The answer, when it finally came, was not one answer but 2, and one of the 2 explains where some of the heaviest matter on this planet came from. 50 years is a long time in a field that measures its progress in decades. People began their careers on this problem and retired before it was settled. At least one of the arguments about it was formally staged in front of an audience in Washington, with two physicists taking opposite sides, because the evidence genuinely would not decide between them. For a long stretch in the middle of all that, the best physics available said flatly that the thing could not exist. Not that it was improbable, or that some number had come out wrong, but that whatever was producing this light should have been physically incapable of letting it escape. There is something quietly strange about the fact that anyone was watching at all. This has been going on for 13 billion years. The light arrived first at a planet with nothing living on it, and then at a planet with oceans. Later, it arrived at a planet full of animals whose eyes had never had any reason to evolve a sensitivity to that part of the spectrum. It has been passing through this room and through you for far longer than there have been rooms. We have been able to notice it for not quite 60 years. The universe did not begin doing this because we turned up to watch. We simply became, quite recently, the part of it that looks up. Before we go back to where all of this actually started, there is one small thing. If these long nights are worth returning to, subscribing is how they find their way to you without any effort on anybody's part. And if the mood is right, leave a comment saying where you are listening from and what the hour is there. Every one of them gets read, and there is something genuinely lovely about knowing that this is playing in 30 time zones at once, in rooms that nobody at this end will ever see. The story does not begin in Sagitta though, and it does not begin with any of the instruments that were briefly overwhelmed there. It begins 55 years earlier, in the middle of the Cold War, with a pair of small satellites that were launched to watch for the end of the world and found something considerably larger instead. They were not much to look at. Each one had 20 faces like an oversized die, 19 of them covered in solar cells, and the 20th left clear for the exhaust of the motor that would push it into position. At the 12 corners sat detectors for X-rays. Deeper inside, packed and shielded, were counters for gamma rays and for neutrons, which are the two things a nuclear weapon produces in quantities that nothing else in human hands can approach. The program was called Vela, shortened from the Spanish word for a watchman, the one who stays awake through the night while everybody else does not. 12 of them were built in the end by a contractor called TRW, and they were always launched 2 at a time. A gamma ray counter, it is worth saying, holds no opinions about what it is counting. It registers particles arriving and notes down when they arrived, and the question of what those particles were doing before they got there is somebody else's problem later, on the ground. The reason they existed was a treaty. In the summer of 1963, the United States, the Soviet Union and the United Kingdom had agreed to stop testing nuclear weapons in the atmosphere, underwater and in space. Testing underground was still permitted, which meant that the treaty's real difficulty was never the prohibition, but the checking of it. An underground detonation announces itself to seismometers on the other side of the planet, whether anybody wants it to or not. A detonation in space announces itself to almost nothing at all, unless somebody has arranged in advance to be listening. The first pair went up on the 17th of October 1963, 1 week after the treaty came into force. They flew very high, roughly 96,000 kilometers out, far beyond the belts of trapped radiation that surround the Earth, and they were placed on opposite sides of the planet, so that between the two of them there was no direction in which you could hide a flash. What Los Alamos had built into those instruments was the ability to recognize a particular shape. A nuclear explosion in space delivers a very sharp pulse of gamma radiation, and then a decline, smooth and reasonably quick, as the products of the reaction spread and cool. There is nothing subtle about the profile. It goes up almost instantly, and then it comes down. And on the way down, it does not do anything else. On the 2nd of July, 1967, one of the satellites recorded a flash of gamma radiation that lasted about 10 seconds and had entirely the wrong shape. There was a spike, then there was a dip, and then a second spike, and then a long, unhurried decline that took its time about finishing. No weapon anybody had designed, or could design, produces a profile like that. A bomb does not stutter. Consider what that put in front of the people on shift. It was the middle of the most heavily armed decade in human history, and an instrument built for the sole purpose of detecting a nuclear detonation had detected something that was demonstrably not a nuclear detonation. It was not the sun either, which was in the wrong part of the sky and does not behave in that manner under any circumstances. Where it had come from was unknown. What had produced it was unknown. The one thing the flash established with real confidence was that nobody had broken the treaty. So nothing was said about it. Some of that was the obvious problem. The readings belonged to a weapons program and could not simply be posted to an astronomer. Some of it was the ordinary caution of people who have worked with instruments for long enough to know that a single strange reading is, 9 times out of 10, the instrument. 2 years later, a Los Alamos physicist named Ray Kleber-Seidel began going back through the accumulated records looking for more of them. His method was patient and unglamorous. A genuine event out in space should register on several widely separated satellites at almost the same moment, whereas a fault in the electronics should register on exactly one. So he searched for coincidences. The flash from July of 1967 stood out at once, and between July of 1969 and July of 1972, working alongside Ian Strong and Roy Olson and a set of programs written to comb the archive automatically, they collected 16 more. By then, the newer satellites were flying and they were considerably better. Vela 5 went up in May of 1969, and the pair were positioned 180 degrees apart at a distance of roughly 118,000 kilometers from the center of the Earth. That put something like 230,000 kilometers between them, which is well over half the way to the Moon, and it quietly converted a fleet of separate spacecraft into a single instrument. Light takes about 0.8 of a second to cross a gap of that size. If a flash reaches one satellite slightly before it reaches another, the size of that delay tells you the angle the light arrived at. And with several satellites, several angles, and a great deal of arithmetic, the angles cross and a direction falls out. The directions did not point at the Earth. They did not point at the Sun. And no two flashes ever came from the same place twice, which quietly disposed of the idea that some single object somewhere nearby was simply misbehaving on a schedule. In June of 1973, the three of them published a short paper in the Astrophysical Journal under a title of almost aggressive restraint: Observations of Gamma-ray Bursts of Cosmic Origin. 16 events. No mechanism proposed, no distance offered, no source suggested, and virtually no speculation of any kind. The word carrying the entire weight of that title is cosmic, and all it is claiming is that these did not come from anywhere you could point to on a map of the world. The reaction was immediate and fairly chaotic. Within a decade, there were more published theories about what caused these flashes than there were confirmed examples of them. Comets falling onto neutron stars, antimatter drifting into ordinary matter, white holes, collisions between objects that nobody had ever actually observed. Almost every one of those ideas was wrong, and had to be, because there was nothing available to test any of them against. What was genuinely known at the end of all of it would have fitted on the back of an envelope. The flashes were real. They arrived from somewhere outside the solar system, and they never came twice from the same place. How far away they were, how large, how any of it worked, all of that remained completely open, and it stayed open for another 18 years, until somebody finally put an instrument into orbit that could watch the whole sky at once and do nothing else but wait. It went up on the 5th of April, 1991, in the cargo bay of the Space Shuttle Atlantis, and at 17 tons, the Compton Gamma Ray Observatory was the heaviest object anybody had yet carried into orbit for the sole purpose of looking at the sky. That record would stand for another 8 years. 4 instruments were bolted to it, and the one that matters here was in some ways the crudest of the 4. 8 detector modules, 1 at each corner of the spacecraft, built at the Marshall Space Flight Center in Alabama and given the name Burst and Transient Source Experiment. 8 corners meant that whichever direction a flash came in from, at least one module was facing it. Comparing the brightness across all 8 gave a rough position, a few degrees at best, which is poor by any standard in astronomy. In exchange, the thing never had to stop and aim, and it never looked away. Almost everybody knew what it was going to find. The settled view through the 1980s was that these flashes came from neutron stars inside our own galaxy, the small, dense remnants left behind when massive stars collapse. The Milky Way contains a great many of them, and they sit where nearly everything in the Milky Way sits, in the flat disk. A disk viewed from inside it is a band across the sky. So the test was clean and required no cleverness at all. Plot a few hundred burst positions and watch them crowd along the same stripe the Milky Way already occupies. If you have ever seen that band from a dark site, that is exactly where they should have been. A few degrees of accuracy was more than enough to see a stripe. The first results were announced in the autumn of 1991, and there was no stripe. The bursts were scattered across the sky with an evenness that bordered on the unreasonable. They showed no preference for the plane of the galaxy and no crowding toward its center. When the first 1,000 or so were tested properly for lopsidedness and then for any subtler 4-way structure underneath that, every number came back consistent with nothing at all. The distribution was perfect and perfectly useless. The result was not so much disputed as quietly declined. That October, at the first major meeting on the subject after the announcement, most of the theoretical talks were still about neutron stars in the galactic disk. People had spent whole careers on that picture. It took a while for the room to accept that the sky had just said no to it. The difficulty with a perfectly even sky is that it is not one answer but 2. And the 2 are about as far apart as answers get. Picture the exact center of a small spherical room where the walls sit the same distance away in every direction. Now picture standing somewhere, anywhere, in a fog that reaches further than the eye can see, where the view is also identical whichever way you turn. Isotropy establishes that you are in one of those 2 situations. It has nothing whatsoever to say about which. A second clue sat in the data, and it was almost as ambiguous. Imagine sources of a fixed brightness spread evenly through space and going on without end. Counting them is then simple arithmetic. Look twice as far out, and the volume being surveyed grows 8-fold, so 8 times as many should turn up. What the 8 detectors actually found was a shortage. The faint bursts, meaning the distant ones, were fewer than an endless uniform distribution demands, and that shortage means the population has an outer boundary. Whatever these things were, at some distance out, they stopped. Donald Lamb, at the University of Chicago, had a way of accommodating all of that without leaving the neighborhood, and it deserves to be taken seriously, because it was serious. Neutron stars are not born gently. The supernova that produces one is lopsided, and the newborn object is flung away from the wreckage at speeds measured in hundreds of kilometers per second, sometimes 600 or 700, occasionally more. That is comfortably enough to escape the galactic disk altogether. Give a population of them a few 100 million years to spread out, and what gathers around the Milky Way is a roughly spherical cloud of old, fast, faint neutron stars. Seen from a planet sitting well inside such a cloud, it looks the same in every direction. It also has an outer edge, which accounts for the missing faint bursts without any further argument. The energy budget was what made the halo picture so appealing. If these flashes were a few 100,000 light-years away rather than billions, each one needed to release roughly what the Sun puts out over 8 years. That is an enormous quantity by any measure a person can hold in mind, and a thoroughly unremarkable one for a star. Nothing new had to be invented to supply it. A starquake in a crust under strain that nothing on Earth can approach would do it, or a comet falling onto a neutron star's surface. Bohdan Paczynski at Princeton looked at the same two facts and drew the opposite conclusion. His version was in one sense the lazier of the two, and in every other sense the more uncomfortable. The universe on its largest scales is even in every direction. That is among its better established properties. So if the bursts are spread through the universe at large, isotropy stops being a clue that needs explaining and becomes simply what the sky looks like from anywhere in it. The shortage of faint bursts stops being an edge in space as well, and becomes what happens when the light of very distant things is stretched and dimmed by the expansion of the universe on its way over. Both observations fall out of the cosmological picture without anyone having to arrange them. The price was the energy. At those distances, every one of these flashes had to release something close to what the Sun will produce across its entire 10 billion year life, and deliver it in a matter of seconds. Between the two proposals, then, sat a factor of about 1 billion. The same flash, the same 8 detectors, the same figures on the same page, read one way or read the other. Paczynski's position amounted to something quite bracing. The data points at the cosmological answer, and if nobody currently possesses a mechanism capable of releasing that much energy that fast, then nobody currently possesses one. The halo model had a pressure point of its own, and it was geometric. The Sun does not sit at the middle of the Milky Way. It sits about 25,000 light-years out from the center, which means anything arranged as a sphere around the galaxy ought to look slightly lopsided from here, with a few more bursts toward the center than away from it. The search for that lopsidedness went on for years and never found it. The only remedy was to make the halo larger, and then larger again, until the shell of neutron stars had to reach roughly halfway to Andromeda. At that size, it was no longer obviously a feature of our galaxy at all. On the 22nd of April, 1995, the two men went to Washington and argued it out in front of about 350 people in the Baird Auditorium of the Smithsonian's Natural History Museum. The choice of room was not an accident. 75 years earlier, almost to the day, Harlow Shapley and Heber Curtis had stood in that same auditorium and argued over whether the faint spiral smudges visible in the telescopes of the day were clouds of gas inside the Milky Way or separate galaxies far beyond it. Curtis turned out to be right. 3/4 of a century later, in the same room, two more physicists were arguing about whether another set of objects lay inside our galaxy or outside it. The 1920 event had been billed as the scale of the universe. The 1995 one was called the distance scale to gamma-ray bursts. Nobody won that evening. Both men published written versions afterward, and if you read them now, the striking thing is how good both arguments are. Each had a coherent physical picture. Each accounted for everything the detectors had measured. Neither could produce the single piece of evidence that would have ended it. The audience went home entertained and no more certain than when it arrived, and the two of them went back to work. What the argument needed was never going to be a better statistic. By the time the observatory was deliberately brought down out of orbit in the summer of 2000, it had recorded 2,704 bursts, and the map had only become smoother and more featureless as the count climbed. Not one of those flashes ever said how far away it was. Counting could not settle this. What was required was for a single burst, just one, to leave something behind. Some residue that stayed in the same patch of sky for longer than a few seconds. Long enough for an ordinary telescope working at ordinary wavelengths to find it and hold it and read what was written into it. The solution, when it finally came, had nothing to do with building a better gamma-ray detector. It came from giving up on the gamma rays entirely, or at least from demoting them. A burst lasts seconds and arrives with almost no positional information attached, and 30 years of trying to squeeze a location out of that had produced very little. The idea that worked was to stop chasing the flash and start hunting for whatever it left behind afterward, on the assumption, which was a guess and by no means an obvious one, that something would be left behind at all. The satellite built around that idea was an Italian program with substantial Dutch participation, launched from Cape Canaveral on the 30th of April 1996 into a low, almost perfectly equatorial orbit 600 kilometers up. After launch, it was renamed for Giuseppe Occhialini, a physicist who had spent part of the 1930s in the Cavendish Laboratory and part of the war years hiding in the mountains of Brazil, and who was known to more or less everybody as Beppo. The satellite has been called Beppo-SAX ever since. What made it different was the arrangement of instruments rather than the quality of any one of them. It carried a gamma-ray burst monitor, which did the same job as everything that had come before and did it no better. It also carried 2 wide-field cameras, which watched a large piece of sky in X-rays and could image whatever happened there. And it carried a set of narrow-field X-ray telescopes, which saw only a tiny patch but saw it sharply. The whole thing was tied together by the ability to turn. When the monitor registered a burst, the wide-field cameras could produce a position accurate to a few minutes of arc rather than a few degrees, and the spacecraft could then swing around and stare at that spot with the narrow instruments while the memory of it was still warm. The difference between degrees and arc minutes is easy to underrate. A position good to a few degrees describes a patch of sky many times wider than the full moon, and no large telescope on Earth can usefully search an area like that because large telescopes see a keyhole. A position good to a few arc minutes is a patch a telescope can actually be pointed at and worked through. On the 28th of February 1997, at 2 minutes to 3 in the morning Universal Time, the monitor triggered. The wide-field cameras had the burst in frame. 10 months after launch, the machine did exactly the thing it had been arranged to do. 8 hours later, the narrow-field telescopes were brought round onto the position, and Enrico Costa and his colleagues found something sitting in it. A source of X-rays that was not on any earlier map of that part of the sky, and which had not been there in any previous observation. Over the following days, they watched it fade. It was not the burst. The burst was long finished. This was something the burst had left lying around, cooling off in public in a fixed spot for hours and then days. 21 hours after the flash, on the island of La Palma in the Canaries, the William Herschel telescope was pointed at the X-ray position. Jan van Paradise and his collaborators found a point of visible light there. Photographed again on subsequent nights, it was measurably dimmer each time. There was nothing dramatic about the images. A faint dot, growing fainter, embedded in a small smudge of extended light that nobody could yet identify. It was the first time in 30 years that anyone had looked at a gamma-ray burst with an ordinary telescope at ordinary wavelengths and seen anything whatsoever. That cascade is the entire mechanism of what followed, and it is worth being precise about the arithmetic. A gamma-ray monitor gives degrees. An X-ray camera narrows that to arc minutes. An optical telescope narrows it again to arc seconds. From the first step to the last, the patch of sky under suspicion shrinks by a factor of roughly 10,000 in width, which is about 100 million in area. At the far end of that chain, you are no longer looking at a region, you are looking at an object. 10 weeks later, on the 8th of May, Another burst went off, and this time the chain ran all the way through. The optical counterpart was found within a day. On Mauna Kea, the 10-meter Keck 2 telescope turned toward it, and its low-resolution spectrograph took the light apart into its constituent wavelengths. What Mark Metzger and his colleagues found in that spectrum were 8 dark lines. Every element absorbs light at its own fixed set of wavelengths, a pattern as particular as a signature and identical wherever in the universe you find it. When a cloud of gas sits between a bright source and a telescope, it strips out exactly those wavelengths and leaves gaps in the spectrum. What Keck recorded were the gaps belonging to iron and to magnesium, but not where iron and magnesium put them in a laboratory. Every one of the 8 was displaced toward the red end, all by the same proportion, which is what the expansion of the universe does to light that has been traveling for a very long time. The logic that followed is elegant, and it is also cautious in a way that made it impossible to argue with. The gas doing the absorbing lies in front of the source, so whatever produced the burst had to be at least as distant as that gas, and probably further. The number was not a measurement of where the burst was. It was a floor beneath it. The floor sat at a redshift of 0.835, and a separate absence in the spectrum put a ceiling on it as well, somewhere below 2.3. A floor was more than enough. Light arriving with that much stretch in it has been traveling for something in the region of 7 billion years. It left its galaxy well over 2 billion years before the Sun and its planets began to condense out of a cloud of gas, and it had been in transit for most of the age of the universe by the time it reached a mountaintop in Hawaii. The largest halo of neutron stars anybody had been prepared to propose reached about halfway to Andromeda. This was more than 5,000 times further out than that. The argument was over. Not settled by a better statistic and not conceded by anyone. Simply closed by 8 dark lines in a spectrum taken on a single night of a fading dot that had been located by handing the same patch of sky down from one kind of telescope to another until the patch was small enough to hold something in. And the answer immediately produced a worse question. The energy figure that had made the cosmological picture so uncomfortable was no longer a hypothetical price that might have to be paid. It was now simply the bill. Every one of these flashes really was releasing something close to the Sun's entire lifetime output in a matter of seconds, and there was still no mechanism anywhere in physics that could produce that. There was also a second difficulty, less obvious at first and considerably more serious, which came from looking not at how much light was arriving, but at how quickly the brightness of it changed while it did. Plotted as brightness against time, the trace a gamma-ray burst leaves behind looks less like a bell curve and more like a mountain range sketched by somebody in a hurry. A jagged run of spikes and gaps, some tall and narrow, some broad, some crowded so tightly together that the trace never gets back down to the baseline between them. The flash of July 1967 had that shape, which is precisely what marked it out as something other than a weapon. Every burst logged since has had some version of it, and by the time the 8 detectors on the Compton Observatory had gathered a couple of thousand of them, the pattern was beyond dispute. What mattered was not the overall shape. It was the sharpness of the individual spikes. The fastest of them rise and fall not in seconds but in thousandths of a second. There is a rule that applies to that, and it is among the more useful rules in astronomy because it works on anything at all, of any size, anywhere. Nothing can appear to change faster than light can cross it. Picture a stadium at night with every floodlight burning, and imagine that all of them are cut at precisely the same instant. From the far side of the ground, the lamps nearest you go dark first, and the ones on the opposite touchline a fraction of a moment later, because their light has further to come. The switch was thrown once, cleanly. What arrives is a fade, and the length of that fade is nothing more than the time light needs to travel the width of the stadium. There is no way to sharpen it. The geometry does the smearing whether anyone wants it to or not. So the sharpness of a flicker puts a ceiling on the size of whatever produced it, and the ceiling is not negotiable. Light covers about 300 kilometers in 1,000th of a second. Bursts flicker faster than that. The region doing the emitting can therefore be no more than a few hundred kilometers across, and for the sharpest structure in the sharpest bursts, something closer to 100. 100 kilometers is a distance most people already have a feel for, though rarely in this setting. It is the height of the sky. Straight up from wherever you happen to be sitting, 100 kilometers is roughly where the atmosphere gives out and space is conventionally agreed to begin. That is not a feature of the object. That is the whole object. Set that beside the other figure. This is a region small enough that you could drive across it in an afternoon if it were laid flat on the ground, and for a few seconds it produces more light than every star in the galaxy surrounding it, added together. The Sun is 700,000 kilometers from its center to its surface, and by this standard the Sun is a large, slow, unremarkable object. The obvious question is how anything assembles that much energy that quickly. That question is genuinely hard, and it took a further 25 years to answer with any confidence. The question that stopped people cold in the late 1990s was a different one, and considerably more serious. It had nothing to do with how the light was made. It was about how the light got out. Photons ordinarily ignore each other. Two beams crossing in a dark room pass straight through one another without the slightest interference, which is the only reason it is possible to see across a lit room at all. That courtesy has a limit, and the limit is energy. When two photons meet with more than about 1 million electron volts of energy between them, a shade over 1 million to be exact, a new option opens up. They are permitted to vanish and leave behind, in their place, an electron and a positron, its antimatter twin. The light stops being light and becomes matter. Matter is not transparent. Ordinary daylight cannot do this. A photon of visible light carries a couple of electron volts, roughly 1 million times too little to qualify. Gamma rays carry almost exactly the required amount. The trap is set specifically for them. Whether the photons actually find each other depends on how tightly they are packed together, and this is where the two measurements collide. Take the luminosity that the redshift had just made compulsory. Confine it inside a sphere 100 kilometers wide. The resulting photon density is not simply high. It is high enough that a gamma ray attempting to leave has effectively no prospect of reaching the edge without meeting another one on the way out. Run that calculation properly for a burst at cosmological distance, and the figure that falls out is around 10 trillion. That is the optical depth to pair production, and what it means is that a gamma ray created anywhere near the middle would be absorbed and converted into particles, something on the order of 10 trillion times over before it could escape. A place like that is not a source of gamma rays. It is a furnace with the lid bolted down. Radiation confined inside an opaque medium scatters and degrades until it has forgotten whatever it originally was, and what finally leaks out through the surface carries no memory of the violence underneath. It emerges as a smooth, featureless glow of the kind any hot, opaque object gives off, whether a furnace or the surface of a star. Above roughly 500,000 electron volts, there should be nothing whatever, because everything above that line is exactly what the trap consumes first. The spectra coming out of the detectors looked nothing like that. They were hard and structured, running as power laws rather than smooth curves, and they carried on well past 500,000 electron volts into territory that should have been sealed shut. The photons arriving above the atmosphere were, without exception, the ones with the least business having survived the journey out of their own source. None of this was fresh news. Malvin Ruderman had identified the difficulty in 1975, and Martin Schmidt had arrived at the same wall by a different road. For 20 years it caused no particular damage because the severity of the problem scales with the luminosity, and the luminosity depends entirely on the distance. At halo distances, the numbers were uncomfortable, but survivable. The compactness problem was, in fact, one of the stronger arguments for keeping these objects close to home, and it had been deployed that way in Washington. What the 8 absorption lines did was remove that shelter. By the summer of 1997, there were 3 statements on the table, each resting on direct measurement, and no 2 of them were in any difficulty at all. The source is smaller than 100 kilometers across because it flickers in milliseconds. The source is billions of light years away because its light arrives stretched. The gamma rays are getting out because they are landing in the detectors. Any 2 of those can be held together without strain. All 3 at once, according to every piece of physics available at the time, could not be happening. It is worth staying with that a moment because it is not a closed episode from 30 years ago. It happens roughly once a day. Somewhere above the atmosphere, at this hour, gamma rays are arriving from a region about the width of the sky above your head, on the far side of most of the observable universe, having got out of somewhere they had no physical means of getting out of. There was a way through, and its outline had been visible since Ruderman first drew the trap. It does not involve making the source larger or fainter or more distant. All 3 had been attempted, and none of them survives contact with the measurements. The only route out is to stop treating the source as an object sitting still and being observed. Everything changes if the material producing the light is not stationary at all, but tearing toward the observer at very nearly the speed of the light coming off it. That single alteration rescues every number on the page. It also requires a region 100 kilometers wide to accelerate a serious quantity of matter to within a hair of the speed of light in under a second, which is why, for a long time, nobody was in any hurry to suggest it. The gamma rays in a gamma ray burst are not gamma rays at the place where they are made. They become gamma rays on the way, and the thing that converts them is nothing more exotic than speed. Light emitted by something rushing toward an observer arrives with its energy raised. It is the same effect that lifts the pitch of an approaching siren, transferred from sound to light and pushed to speeds where it stops being a subtlety and becomes the dominant fact in the room. Material traveling toward the Earth with a Lorentz factor of 100 lifts the energy of everything it emits by roughly that factor. So a photon landing in a detector with 1,000,000 electron volts of energy did not leave its source carrying 1,000,000 electron volts. It left carrying something nearer 10,000. 10,000 electron volts is an X-ray. It is unremarkable light, the sort used to photograph a broken bone in your wrist. 2 X-rays meeting head-on have nowhere near enough energy between them to convert into an electron and a positron. The threshold is not approached, let alone crossed. Inside the moving material, where the photons and the particles all share the same headlong rush, nothing dangerous is happening at all. The trap that had sat in every calculation for 20 years never springs, because in the only frame that matters, the photons capable of springing it are not there. They are gamma rays purely in our accounting, and only because of how fast the thing producing them is coming at us. That is one of 2 rescues, and the second is geometric. The argument about the stadium assumed a stadium standing still. A source charging toward the observer is pursuing its own light, so the light released at the end of a flicker has less ground to cover than the light released at the start, and the gap between their arrivals is compressed. The compression goes as the square of the Lorentz factor, which, at 100, means a factor of 10,000. A flicker lasting 1,000th of a second no longer confines the source to a few hundred kilometers. It allows several million, a region comfortably larger than the Sun. Spread the same light through a volume that much bigger, and the photon density collapses, and with it, any prospect of two photons finding one another. Put the two rescues together, and the opacity falls not in proportion to the speed, but as roughly the sixth power of the Lorentz factor. 100 raised to the sixth power is a trillion, which is why the resolution of the compactness problem is not a vague statement about things moving quickly, but a hard floor with a number attached, at least 100, and in the brighter bursts several times that. A Lorentz factor of 100 corresponds to 99.995% of the speed of light. Figures with that many nines in them stop conveying anything, so it helps to convert. If you set that material off alongside a beam of light, then after 1 full second of travel, the light would be ahead by 15 kilometers. After a year of running, the light would be ahead by about 26 minutes. A cost comes attached to all this, and it is a harsh one. The energy carried by matter moving at a given Lorentz factor is simply the mass multiplied by that factor, multiplied by the speed of light squared, and the energy had already been fixed by the redshift measurement, so the mass was no longer a free choice. Running the arithmetic backwards gives a total quantity of matter in the outflow of a few millionths of the Sun's mass. In more familiar terms, about 2 Earths. That is the entire ejector, everything thrown outward by the explosion, weighing what a couple of small planets weigh, carrying the energy the Sun will spend across 10 billion years. The constraint cuts in both directions because extra matter absorbs the energy rather than being flung by it. Load the outflow with any appreciable amount of ordinary debris and the Lorentz factor drops. The trap closes again and nothing escapes. Whatever machinery produces these events has to be prodigiously energetic and, at the same time, almost surgically clean. The picture assembled around all of this has a name, and the name is older than most of the evidence supporting it. In 1986, 9 years before he stood up in a Washington auditorium to argue for cosmological distances, Bohdan Paczynski published a short paper working out what those distances would demand. Jeremy Goodman arrived at nearly the same place independently and at nearly the same moment by asking whether gamma-ray bursts were optically thick and concluding that they had no choice but to be. Both men were describing the same object. They called it a fireball. The word is not decorative. Deposit the Sun's lifetime output into a region the size of a city in under a second, and what forms is a plasma so hot and so dense that ordinary categories stop applying. It is made of radiation, and of electrons and positrons appearing and annihilating and appearing again, at temperatures where the difference between light and matter is close to a bookkeeping distinction. The radiation pressure inside is higher than anywhere else known. Something like that cannot stay where it is. It expands, and as it expands, its own radiation pressure drives the material outward, and its internal heat converts into bulk motion. That conversion is the essential move. The fireball cools as it accelerates, spending temperature to purchase speed, and by the time it has swollen a few hundredfold, it is no longer especially hot. It has become a thin shell coasting outward at very nearly the speed of light, carrying almost all of the original energy and carrying it invisibly as motion, which creates a fresh difficulty. Kinetic energy does not shine. A shell coasting through empty space at that speed radiates next to nothing because there is nothing to push against and nothing left inside it to glow. All the energy is present and none of it is emerging. Something has to turn it back into light. The answer Martin Rees and Peter Meseros published in 1994 rests on a single assumption about the central engine, and the assumption is only that the engine is not smooth. Nothing that violent runs steadily. If whatever sits at the center throws material out in fits and starts, then the shells leave at slightly different speeds, and a shell launched a moment later at a marginally higher Lorentz factor will slowly gain on the slower one ahead of it. Given enough distance, it arrives. What follows is a collision between two masses of material both traveling at very nearly the speed of light and differing only in how nearly. By the standards of the speeds involved, it is a gentle nudge. By every other standard, it is catastrophic. Shock fronts form. Electrons in the shocked material are accelerated to enormous energies and spiral through the tangled magnetic fields carried along in the flow, and spiraling electrons radiate. In the moving frame, what they produce is X-rays. In ours, it is a spike of gamma rays. This is the part worth holding on to. One collision makes one spike. The jagged trace a burst leaves on a detector is a record of when the shells were launched and how fast each of them was going, which is to say, it is a record of what the engine was doing, instant by instant, while it was doing it. When you look at one of those light curves, you are not looking at a summary. The stutter in the light is the engine's own stutter, and it has crossed 7 billion years without being smoothed or averaged or edited, and it arrives with its timing intact. Eventually, the shell runs out of other shells to strike and begins hitting something else. Ahead of it lies the ordinary matter of the neighborhood the star lived in, thin interstellar gas, or the wind the star had been shedding for millennia before it died. It is close to nothing by any earthly measure and an immovable wall at these velocities. Plowing into it drives a second kind of shock, this one at the leading edge of the entire outflow, and this shock does not switch on and off. It builds, and then it fades slowly as the shell is dragged to a halt over days and weeks. That deceleration is what shapes an afterglow. As the shell slows, its Lorentz factor falls, and the characteristic energy of the light it produces falls in step, so the emission slides steadily down the spectrum. What starts as X-rays becomes visible light, then infrared, then radio, across hours and days, and eventually months. It is why the narrow-field telescopes found something at 8 hours, why the counterpart on La Palma appeared at 21, and why radio astronomers are sometimes still watching the same patch of sky a year later. The framework holds up well where it can be tested hardest. For the afterglow, where the physics is comparatively clean and the predictions run for weeks, it works. For the burst itself, the part with the spikes in it, it remains a working picture rather than a settled one. Internal shocks are inefficient on paper, converting only a small fraction of the available energy into light, and there are serious competing accounts in which magnetic fields do the work instead. How a gamma ray burst actually makes its gamma rays is, after more than 50 years, still an open question. One further consequence follows from all that speed, and it is the one that overturns the largest number on the page. Radiation from material moving with a Lorentz factor of 100 does not leave in all directions. It cannot. The same motion that raises the photon energies also sweeps the emission forward into a narrow cone with an opening angle of roughly 1 divided by the Lorentz factor, which at 100 comes to about half a degree. Not one of the energy calculations made up to that point had allowed for this. Every one of them assumed a sphere. Two different kinds of narrowness had entered the problem at the same moment, and for several years there was no way to tell them apart. The first is a viewing effect and nothing more. Material racing toward an observer sweeps the light it emits into a forward cone, so that even a fireball expanding as a perfect sphere would only ever be visible in one small patch, the patch that happens to be coming straight at the telescope. Everything else on that sphere is moving sideways relative to the line of sight, and its light is thrown somewhere else entirely. Nothing about this reduces the total energy. A spherical explosion still spends everything it has in every direction. It simply cannot all be seen at once. The second kind of narrowness is a fact about the object rather than about the observer. If the outflow is not a sphere at all, but a genuine jet confined to a wedge of sky, then the energy is not being spent in every direction, and every calculation that assumed otherwise has been overcharging by an enormous margin. The difficulty is that early on the two look identical. While the Lorentz factor is still high, the visible patch is far smaller than the jet containing it. An observer looking at a narrow cone of material through an even narrower window sees no edges and no boundaries, only glowing material filling the field of view in every direction available. A jet at that stage is indistinguishable from a sphere. There is nothing in the data to separate them. What separates them is time and the fact that the blast wave slows down. As the Lorentz factor falls, the visible window opens wider. At first, it opens into more of the jet, and the afterglow behaves exactly as a spherical explosion would. Then comes the moment when the window has widened to match the jet itself, and after that, every further widening reaches into empty space where a sphere would have supplied more emitting material, and a jet supplies none. The light curve, which had been fading steadily, begins to fade noticeably faster. The jet also starts to spread sideways at about this point, which steepens the fall further. The signature is unmistakable once anybody knew to look for it, because it happens at every wavelength simultaneously. Radio, optical and X-ray all turn the same corner at the same hour, which no other process does, and the timing carries the information. The sooner that corner arrives, the narrower the jet must have been. In 2001, Dale Frail and a group of collaborators went through every burst for which a well-monitored afterglow existed, most of them tracked in radio at the Very Large Array in New Mexico, and followed in the optical from the ground, and read the opening angle out of each one. The answers ran from about 2 degrees to about 20. The middle of the distribution sat at 7. 7 degrees is worth pausing on because it is not an abstraction. Hold your fist out at arm's length and it covers roughly 10 degrees of sky. The entire output of the most energetic events in the universe is being poured into a cone rather narrower than that, twice over, once in each direction along an axis. A cone that narrow covers about 1 part in 130 of the sky, which means that when one of these goes off anywhere in the observable universe, the odds of the beam containing the Earth are about 1 in 130 and the other 129 times. Nothing arrives at all. That figure is a flaw rather than a best estimate, because the narrowest jets are precisely the ones least likely to be aimed anywhere useful. So the events we are missing are systematically the ones with the smallest openings. Corrected properly for that bias, the true ratio of bursts that happen to bursts that are seen probably runs to several hundred to 1. For every one anybody will ever hear about, several hundred went off unremarked. Picture a very large, dark field at night, with people scattered across it holding narrow-beamed torches. Each one switches on for a second or two, aimed in whatever direction its holder happens to be facing, and then goes out. From where you are standing, only the ones pointed your way are visible at all. There is no means of counting the rest, and no way of knowing they occurred. Every gamma-ray burst ever catalogued belongs to that first group. The entire subject rests on a sample assembled by accident of orientation. The consequences for the energy budget were immediate and enormous. If a burst is spraying its output into 1 part in 130 of the sky, then the figure obtained by assuming a sphere is too large by that same factor. Every headline energy ever quoted for one of these events, including the most extreme, is an isotropic equivalent number, a statement of what the total would have been if the light really had gone out in all directions, which it demonstrably did not. Divide by a few hundred, and for the narrowest jets by closer to 1,000, and what remains is the real energy released. Then came the part nobody expected. The apparent energies of the bursts in that sample spanned about 1,000-fold, from the modest ones to the outrageous. The opening angles spanned roughly 10-fold, and when the 2 sets of numbers were laid alongside each other, they turned out to be anti-correlated. The bursts that looked most violent were, almost without exception, the ones with the tightest jets. The ones that looked ordinary had wide ones. Multiply each apparent energy by its own beaming correction, and the spread does not merely shrink, it very nearly disappears. Nearly every burst in the sample landed within a factor of a few of the same value, something like a little under half of everything the sun will radiate across its entire existence. Frail and his colleagues called it a standard energy reservoir, and the implication is difficult to overstate. Whatever machinery is producing these events appears to release roughly the same amount of energy every single time. What differs from one to the next is not the size of the explosion. It is how tightly the explosion is focused and which way it is pointing. That number also rescued the whole subject from the edge of absurdity. A little under half the sun's lifetime output is still a quantity that beggars description, but it is no longer a quantity without precedent. An ordinary core collapse supernova, the common sort that goes off in a galaxy like ours once or twice a century, throws off around twice that much in the raw motion of its debris. For 30 years, these things had been demanding energies that nothing in astrophysics could supply. Beaming brought them down into the range of something that already happens regularly all over the universe. They had stopped being impossible and become merely difficult. The tidiness of that 2001 result has softened since. With a larger sample and better afterglow coverage, the clustering is looser than it first appeared, and there is real scatter in the corrected energies rather than a single sharp value. But the central finding has never been overturned. The true energies are vastly smaller than the raw numbers suggest, and vastly more alike. The picture also makes a prediction that can be checked, which is always the useful part. If most jets miss us, then for every burst seen head-on, there should be many pointed slightly to one side, whose gamma rays never arrive, but whose afterglow, once the blast wave has slowed and the visible window has widened, eventually swings into view. Somewhere out there should be a population of fading X-ray and optical and radio sources with no burst attached to them at all. Orphans, arriving without the flash that made them from jets that were never aimed at you or anyone. People have been hunting for those for 2 decades, with the sort of partial success that keeps an argument alive rather than settling it. All of which sharpens a question the data had been answering quietly since 1993, 4 years before anybody knew how far away a single one of these things was. Sorted by the one property that requires no distance, no model and no assumptions at all, simply how long each burst lasts. They do not fall into one group. They fall into 2, and the split is not subtle. Before that can mean anything though, there is an awkward preliminary question to settle, which is what "how long" is supposed to mean. A gamma-ray burst does not start and stop. It emerges out of the background count, does whatever it is going to do, and subsides back into the noise, and the edges of it are a matter of opinion. A faint tail that one analyst calls part of the event, another will call detector background. So a ruler had to be invented, and the one that's stuck is called T90. Add up all the counts the burst delivered from beginning to end. Find the moment when 5% of that total had arrived, and the moment when 95% had. The interval between those 2 moments is the duration. It discards the ragged ends at both extremes, and it produces the same answer regardless of who is doing the measuring, which is the entire point of it. Measure a few hundred bursts that way, take the logarithm so that events lasting a fraction of a second and events lasting a minute can sit on the same axis, and plot how many fall where. What appears is not a single hill with a peak somewhere in the middle. It is 2 hills with a valley between them. One group clusters well under a second, with the middle of it sitting somewhere around 1/3 of a second. The other clusters around 30. The 2 are separated by a factor of roughly 100, and the low point between them falls near 2 seconds. The first sight of this came from an unlikely direction. In 1981, a Soviet team led by Yevgeny Mazets published an analysis of 143 bursts recorded by instruments carried on the Venera probes to Venus, and the duration distribution in that sample already looked suspiciously double-humped. 3 years later, an American group led by J. Norris reported the same suspicion. Neither had enough events to press the case, and the observations sat where such observations tend to sit, in the category of things that are probably nothing. It took the arrival of a catalogue running to thousands of bursts to settle it, and in 1993, Krisa Kuveliotou and her colleagues, working with the first year of data from the 8 detectors on the Compton Observatory, showed that the 2 humps were real. A single histogram, however, is not proof of anything. Detectors have their own rhythms built into them. The instrument searched for bursts on several fixed timescales, the shortest of which was 64 thousandths of a second, and any measuring apparatus with preferred intervals can in principle stamp those intervals onto its results. A gap in a duration distribution is exactly the sort of feature that a trigger threshold might invent out of nothing at all. What made the case is that a second, entirely unrelated property splits at the same place. Spectral hardness is a crude ratio and requires no assumptions whatever. Every detector sorts arriving light into energy channels, and the hardness of a burst is the count in a high channel divided by the count in a low one. A burst weighted toward the top end is hard, one weighted toward the bottom is soft. Sorted by hardness rather than by clock, the same 2 groups reappear. The short bursts are systematically harder, and the energy at which their spectra peak sits somewhere near 500,000 electron volts against roughly 160,000 for the long ones, a difference of about 3-fold arrived at without reference to any duration at all. 2 independent rulers laid across the same catalogue drew the same line. Run the statistics on whether a single population could produce both distributions by accident, and the probability comes out below 1 in 100 million. The proportions are lopsided. In the Compton catalogue, roughly a quarter of the bursts were short, and the remaining 3/4 long. That ratio, it should be said, is not a property of the universe, but of the instrument. Later detectors built with different sensitivities have reported anywhere from 1/10 to 1/5. Short bursts are faint, fast and easy to miss, and every catalogue ever assembled undercounts them by an amount nobody can pin down precisely. The 2-second line itself deserves a warning label. It is a convention, chosen because it happens to sit in the valley, and at the level of any individual event, it means nothing. The distributions overlap. There are genuine members of the long population that finish in 1.5 seconds, and genuine members of the short population that run to 3 seconds, and the line sorts both into the wrong bin without hesitation. What the histogram supports is a statement about groups. There are 2 kinds of object here. What it cannot do is tell you which kind any particular burst is, from its duration alone. That distinction went largely unspoken for a long time, and it eventually caused a great deal of trouble. None of it arrived with an interpretation attached. The paper appeared 4 years before anyone knew the distance to a single one of these objects, which meant it announced a division without being able to say what had been divided. 2 kinds of what exactly? The catalogue was public and the arithmetic was not difficult. If you had pulled the durations down in 1993 and plotted them on graph paper over an afternoon, you would have found the same 2 humps. Finding them was never the hard part. Duration is not a trivial property either, and this is what gave the result its weight. A burst's light curve is a transcript of the engine that produced it, collision by collision, and the length of that transcript is a measurement of how long the engine ran. Something that operates for 30 seconds and something that has finished in 1/3 of a second are not the same machine set to different speeds. They are being driven by processes with fundamentally different natural timescales, and a natural timescale is a clue about size and about mechanism. 1/3 of a second is faster than a human reflex, The entire event would be over before you could react to a light coming on in a dark room. 30 seconds is long enough to be aware of, long enough to speak a sentence in, and long enough, as it turned out, to be telling you something quite specific about the thickness of a star. There were 2 clocks. In 1993, nobody could see what either of them was attached to, and the answers, when they eventually came, were not related to one another in any way at all. The 2 populations turned out to share a name only because the same detectors happened to catch them both, and because gamma rays look much the same regardless of what made them. The longer of the 2 stories begins inside a star that has run out of everything it needs in order to keep living. A star is an argument between 2 forces, and for most of its existence the argument is a stalemate. Gravity pulls every part of it toward the middle. Fusion in the core releases energy that pushes back. Neither wins, and the standoff is what a star actually is. Not a burning object so much as a balance that happens to glow. What ends a star is not running out of matter, it is running out of reactions that give more energy than they cost. For a star of around 25 times the Sun's mass, that whole balance lasts about 7 million years, and it comes apart in stages that accelerate alarmingly. Hydrogen fuses into helium for millions of years. When the hydrogen in the core is gone, the core contracts, heats, and starts fusing helium into carbon and oxygen, and that phase lasts a few 100,000 years. Carbon burns for about 10,000. Neon burns for roughly 6 months. Oxygen goes in something under half a year. Silicon, the last rung, is consumed in a matter of days. By the end, the star has arranged itself into concentric shells like the layers of an onion. Hydrogen outermost, then helium, then carbon, oxygen, neon, silicon, with each layer the ash of the one outside it, and at the very center, a ball of iron a few 1,000 kilometers across, weighing more than the Sun. Iron is where the accounting reverses. Every fusion reaction up to that point releases energy because the resulting nucleus is more tightly bound than the ingredients. Iron is the most tightly bound nucleus there is. Fusing it consumes energy rather than producing it, so the moment the core becomes iron, the star has nothing left to push back with. The iron ball is held up only by the reluctance of its own electrons to be crowded together, and that reluctance has a limit. And once the core grows past about 1.5 times the Sun's mass, the limit is reached. What follows takes less than a second. 2 things happen at once, and each makes the other worse. The core is hot enough that its own gamma radiation begins tearing iron nuclei apart back into helium and neutrons, which absorbs energy the core badly needs. At the same time, the pressure forces electrons into protons, converting them into neutrons and releasing a flood of neutrinos that leave immediately, taking the energy with them and removing the very electrons that were holding everything up. The support vanishes, and a ball of iron the size of a small planet falls inward at something like 1/4 of the speed of light, and stops only when the material at the center reaches the density of an atomic nucleus, at which point the strong force stiffens abruptly and the collapse rebounds. That rebound launches a shockwave outward through the infalling material, and what happens next decides everything. In the ordinary case, the shock stalls within milliseconds, exhausting itself against the iron still raining down. If neutrinos streaming out of the newly formed neutron star deposit enough energy behind it, the shock revives, the star is blown apart, and a supernova is the result. The neutron star remains at the center, and the whole business is over in hours. This is the common outcome, and it is common because it works. In 1993, Stan Woosley asked, "What happens when it does not work? If the shock is never revived, or if the star is massive enough that too much material keeps falling back regardless, the neutron star at the center is fed past the mass it can support and collapses again, this time with nothing to stop it. What sits at the center is now a black hole, and the explosion has failed. Woosley's word for the object was a collapser, and his description of it was a failed supernova, which sounds like a disappointment and is nothing of the kind. Without one further ingredient, a failed supernova is genuinely uneventful. The rest of the star falls straight down the hole, and the star simply ceases to be there, quietly, without a flash, a phenomenon that has been searched for, and which appears to happen. The ingredient that changes everything is rotation. Material with angular momentum cannot fall straight in. It has too much sideways motion, and instead of dropping it must spiral, settling into a disk around the equator of the black hole. Whether it does this depends on how fast the core was turning before it collapsed, and rotation is enormously amplified by the collapse itself, in the same way that a spinning skater speeds up on pulling in their arms. A core, a few thousand kilometers wide, turning once an hour, arrives at a radius of 20 kilometers, turning 10 or 20 times a second. The requirement is not that the star be spinning fast by any standard you would recognize. It is that the core retain enough rotation to miss the hole, rather than fall into it. When it does, what forms is the most extreme feeding process in nature. Matter piles into the disk and spirals inward at somewhere between 1,000th and 100th of the sun's mass every second. Several hundred to several thousand Earths per second, for as long as the supply holds out. Over the following minutes and hours, anywhere from 1/10 to several times the sun's mass may fall back and be consumed. The disk is so hot and so compressed that ordinary radiation cannot carry the heat away. It cools by emitting neutrinos in quantities that make the neutrino output of an ordinary supernova look restrained. The energy that eventually drives the jet is now thought to come mainly from the black hole's own spin, extracted electromagnetically by field lines threaded through it and wound up by the rotation, though the details remain a working problem rather than a solved one. The jet is narrow, and it is narrow for a reason that requires no cleverness at all. The disk fills the equator with dense material through which nothing can pass. The only directions with any clear space are the two poles of the rotation axis. Energy released near the hole goes where it can, which is up and down, and the star does the collimating without being asked. The narrowness measured in afterglow light curves is not a property of the engine. It is a property of the room the engine is sitting in, and the room is still standing. This is the part that is easy to overlook. The collapse happened at the center in under a second, and the outer layers of the star have received no word of it. Information inside a star travels at the speed of sound in stellar material, which is quick by human standards and glacial by these, and it will be hours before the surface has any indication that anything has changed. So the jet does not emerge into space. It emerges into the middle of a star that is still, as far as it is concerned, alive, and it has to bore its way out. That drilling takes time, and the time is the answer to a question raised by the shape of the duration distribution. Working through material that dense, the head of the jet advances at a fraction of the speed of light, and crossing the remaining star takes somewhere in the region of 10 seconds. Only after it breaks the surface does anything escape to be seen. So the duration of the burst is not the running time of the engine. It is the running time minus the drilling time. And if the engine shuts down before the jet gets out, nothing is seen at all, anywhere, ever. The distribution of long burst durations in the Swift catalogue shows exactly the flattening at short durations that this predicts. When you read 30 seconds off a light curve, you are reading a length of time that has had the thickness of a star subtracted from it, and the thickness of that star is a distance nobody will ever measure any other way. It also explains why the progenitor has to be stripped. A red supergiant with its hydrogen envelope intact is hundreds of times wider than the Sun, and a jet would be smothered inside it long before reaching daylight. The star has to have shed that envelope already, leaving a bare core roughly the size of the Sun or a little larger, which is precisely the sort of star, hot and stripped and blowing off its outer layers, that astronomers had been cataloguing under the name Wolf-Rayet for a century. Both conditions have to hold at once, and most massive stars fail at least one of them. Stellar winds that strip the envelope also carry away angular momentum, so the same process that solves one requirement tends to ruin the other. Estimates of how many stripped envelope supernovae also produce a burst run from about 1% upward, with a great deal of argument in the range above that. Measured against core collapse supernovae as a whole, the fraction is smaller still. Whether the engine is always a black hole with a disk is also unsettled. A rapidly spinning, intensely magnetized neutron star can drive a jet too, and it accounts nicely for certain features in the X-ray afterglows. What it cannot do is exceed the energy stored in its own rotation, and for a handful of the most extreme long bursts, the total budget runs past that ceiling. For those, nothing but a black hole will serve. If any of this is right, if a long gamma-ray burst really is a large star coming apart from the inside, then the burst should not arrive on its own. The star has been destroyed, and the wreckage of a destroyed star does not stay dark. Weeks later, in the same patch of sky, something else ought to appear. An afterglow and a supernova do not fade in the same way, and that difference is the only reason any of this could be untangled. An afterglow begins bright and declines steadily from the first moment, following a smooth mathematical curve downward as the blast wave slows. A supernova does the opposite. It takes time to brighten because the light comes from radioactive material buried inside an expanding cloud of debris and has to work its way out through the wreckage before anything can be seen. It climbs for 2 or 3 weeks, peaks, and then declines slowly over months. So if a supernova were hiding underneath a fading afterglow, what you would see is a bump. A moment when the decline stopped declining, leveled off, and rose again against all expectation. On the 25th of April, 1998, a burst arrived that was strange from the outset, and it was strange chiefly because it was close. The distance worked out at around 40 megaparsecs, roughly 130 million light-years, which by the standards of this subject is next door and remains the shortest range at which any gamma-ray burst has ever been caught. Within days, a supernova was found inside the error box in a small barred spiral galaxy in the southern sky, and it was there in every sense that mattered. Right position, right week, in a galaxy at exactly the distance the burst's faintness implied. 2 events that rare, appearing in the same place at the same time by coincidence, is not a hypothesis anyone was eager to defend. The supernova itself was unlike anything in the catalogues. Its spectrum, instead of showing the crisp absorption features that identify particular elements, showed broad, shallow troughs where those features should have been smeared out so far that neighboring lines ran into one another. That smearing has a simple cause. The light passes outward through an expanding shell, and different parts of that shell are moving in different directions relative to the observer, some toward, some away, some sideways. Each part absorbs at a slightly shifted wavelength, and since you are seeing the whole shell at once, all those shifts blend into a single wide trough. The width of the trough is a direct readout of how fast the debris is traveling. For an ordinary supernova of this type, the answer comes out around 10,000 kilometers a second. Here it was 3 to 4 times that, above 20,000, and in places considerably beyond. Debris moving at 20,000 kilometers a second would cross the distance between you and the Moon in about 20 seconds. Convert that speed into energy, and the explosion turns out to have carried somewhere between 20 and 50 times the kinetic energy of a standard core collapse supernova. It was also unusually luminous, And the reason a supernova shines at all is worth stating plainly, because it is not the explosion that people are looking at. The explosion is over within seconds. What remains is a cloud of freshly manufactured nickel-56, which is radioactive, and which decays into cobalt and then into iron with half-lives of 6 days and 77 days respectively. Every supernova light curve is, quite literally, a radioactive decay curve seen from a great distance. An ordinary one produces perhaps 7/100ths of the Sun's mass in that isotope. Modeling of this one required something closer to half a solar mass of it. Bohdan Paczynski had recently coined a word for explosions in this class, and Kenichi Iwamoto and his collaborators applied it here: a hypernova. There was, however, a serious problem, and it went unresolved for 5 years. The burst that came with all this was pathetic. Its energy output was somewhere between 1,000 and 10,000 times below that of a normal long gamma-ray burst. The sort of event that, had it gone off at any ordinary cosmological distance, no instrument then flying would have registered at all. So the association was either a magnificent piece of luck, in which a rare supernova happened to sit beneath a rare and feeble burst, or else this was not a normal gamma-ray burst in the first place. That second possibility has never entirely gone away. One proposal is that a class of low-luminosity bursts exists in which the jet fails to punch cleanly out of the star, and what escapes is not a jet at all, but the shock of the explosion itself breaking through the surface. Another is simply that the jet was pointed somewhere else, and this was the spill from its edge. The case was closed by a burst that had nothing peculiar about it at all. At 11:15 in the morning, Universal Time, on the 29th of March, 2003, the High-Energy Transient Explorer registered a burst lasting 21 seconds. It was an entirely conventional event by every measure, and its redshift placed it at about 1/6 of the way back through cosmic history, far enough to be normal, near enough to study. Its afterglow was exceptionally bright, so telescopes took spectra of it every single night. For the first week, those spectra showed exactly what an afterglow should show: a smooth, featureless slope with a few narrow emission lines from gas clouds in the host galaxy sitting on top of it. Then, in the spectrum taken on the 5th of April, something else was underneath. Broad humps had begun rising through the smooth slope, in the same places and with the same widths as the troughs recorded 5 years earlier. Over the following nights, they strengthened as the afterglow beneath them continued to fade, until what remained on the plate was unmistakably a supernova. Krzysztof Stanek's group and Jens Hjorth's group published the identification within weeks of each other. The spectrum was, allowing for distance and dust, very nearly a copy of the 1998 one. Since then, the count has climbed past 60 associations, of which around 29 have been confirmed by spectrum rather than by light curve bump alone. Every single one belongs to the same narrow class. There is no hydrogen in the spectra, which means the star had lost its outer envelope before it died. There is no helium either, which means it had lost most of the layer beneath that as well, and was down to bare carbon and oxygen when the end came. And the lines are always broad. That combination, stripped to the core and moving impossibly fast, is exactly the object the collapsar picture requires, arrived at from a completely independent direction by people looking through optical telescopes at fading dots. The two things are not separate events happening near one another. They are one event, observed through two different geometries. The jet is the fraction of the energy that leaves along the rotation axis, tightly confined, visible only from within a narrow cone. The supernova is what happens to the rest of the star, which is blown apart in every direction and can be seen from anywhere. One is a searchlight, and the other is the fire that the searchlight is mounted on, and whether an observer sees both or only the second depends entirely on where they happen to be standing. What the association does not supply is any guarantee of proportion. Nothing in the physics insists that a more powerful burst be accompanied by a more powerful supernova, and the two are produced by different parts of the same collapse. One by a jet threading the rotation axis, the other by whatever shock manages to unbind the remaining star. The habit of assuming they must scale together was reasonable, widespread, and eventually a source of considerable embarrassment. That, then, was the long half of the problem, solved. An enormous star stripped, spinning, dying badly, with a black hole at the middle of it and a hole drilled through the wreckage. It accounted for the durations, the host galaxies, the energies, and now the supernovae. It accounted for roughly 3/4 of everything the detectors had ever recorded. It said nothing whatsoever about the other quarter. The short bursts, the ones finished in less time than it takes to say the word, had been sitting unexplained since the day they were first separated out, and by now that was very nearly 20 years. Whatever produces a short burst has to finish its work in about 1/3 of a second, and that single requirement eliminates almost everything. A star coming apart is out of the question because a star is too large. Even a stripped one takes 10 seconds simply to let a jet through, and the numbers do not permit 1/3 of a second. Whatever this is has to be small, not stellar, but on the scale of an object that light crosses in a fraction of a millisecond, and it has to have a supply of fuel that runs out almost immediately. There was already an object on the books that fitted, and it had been sitting there since before anybody knew there were two kinds of burst. In 1974, using the 300-meter dish at Arecibo, Russell Hulse and Joseph Taylor found a pulsar whose pulses arrived early for part of each cycle and late for the rest. The explanation was that it was in orbit with something swinging toward the Earth and away again every 7¾ hours, at speeds of hundreds of kilometers a second. The companion was invisible in every waveband, and the mass came out at around 1.5 times the Sun's. It was another neutron star. Because a pulsar is effectively a clock, the orbit could be measured with a precision that no other astronomical system allows. And by 1978, Taylor was able to report that the orbit was shrinking. It was shrinking, moreover, at exactly the rate general relativity predicts for a system radiating away its energy as gravitational waves. The first evidence that such waves existed at all, and the reason the two men received the Nobel Prize in 1993. The two stars are drawing closer by a few meters every year. Extend that inward and the orbit tightens slowly at first, and then with gathering speed, and the arithmetic says that in something like 300 million years, those two objects will arrive. The arrival is worth picturing because it is very fast and very small. Each star is about 20 kilometers across, a city you could walk over in a morning, and weighs more than the Sun. For hundreds of millions of years they circle at a leisurely few meters a year of approach. Then, over the final minutes, the loss of energy accelerates. The orbit collapses, and in the last second they are whipping around one another several hundred times a second at a substantial fraction of light speed, separated by less than the width of a city. In the final milliseconds, the tidal stress becomes greater than the material can bear, and the two objects are torn open and merged. A fraction of a solar mass of neutron-rich matter is thrown out sideways. Whatever remains at the center is too heavy to hold itself up and becomes a black hole, wearing a very small, very hot disk of leftover debris. In 1989, 4 physicists, David Eichler, Mario Livio, Zvi Piran and David Schramm, published 2.5 pages in Nature setting out what such a collision ought to produce. The title of the paper is a list: Nucleosynthesis, Neutrino Bursts, and Gamma Rays from Coalescing Neutron Stars. They argued that the debris flung out of a merger would be so rich in free neutrons that it would manufacture heavy elements by rapid neutron capture, that the collapse itself would emit a flood of neutrinos, and that the small hot disk around the newborn black hole would drive a jet and produce a burst of gamma rays. A gravitational wave signal came along with the package, because that was how the orbit had decayed in the first place. 4 separate signatures from one event, none of which anybody had any means of testing. The fit to the short bursts was uncomfortably good. The disk contains perhaps 1/100th of the Sun's mass, not several tenths, and at the accretion rates involved it is consumed in well under a second. The natural timescale falls out without adjustment. There is no supernova because nothing is being blown apart. The material was already the compressed remains of 2 stars that died long ago. And the whole thing can happen anywhere, in any kind of galaxy, at any time, because the delay between the formation of the binary and its collision runs from tens of millions of years to well beyond the present age of the universe. 9 years later, Li-Shin Li and Bohdan Pajinski worked out what the ejected debris would look like on its own. Neutron-rich matter, once flung free, decays. The heavy nuclei formed in the first seconds are radioactive, and their decay would heat the expanding cloud and make it glow for a few days in the optical and infrared, roughly 1,000 times brighter than a classical nova and rather redder than anything else in the sky. The name for that glow, kilonova, was attached to it a decade afterwards by Brian Metzger and his colleagues. The prediction came first, and it came with a shape and a timescale and a colour, none of which was evidence. The 1989 paper was largely ignored at the time, and its authors knew perfectly well why. There was nothing to check it against. Short bursts had no afterglows, for the entirely practical reason that a burst which lasts 1/3 of a second is over before any satellite can turn around, and by the time a position had been circulated and a telescope pointed, whatever faint glow had followed it was gone. For a decade after the long bursts had been located and measured and explained, the short ones remained exactly what they had been in 1973, flashes with directions and nothing else. The wall came down in the space of 11 weeks. Swift, launched at the end of 2004 specifically to swing around fast, caught a burst on the 9th of May 2005 that lasted about 40,000ths of a second and had its X-ray telescope on the spot within minutes. The position came out to within about 9 arcseconds. Sitting inside that circle was a large, bright, elliptical galaxy, roughly 2.5 billion light-years away. An elliptical galaxy is the decisive detail, and the argument is short enough to hold in your head. Elliptical galaxies finished forming stars billions of years ago. Massive stars live for a few million years at most. Therefore, an elliptical galaxy contains no massive stars, has not contained any for a very long time, and cannot produce a collapser under any circumstances whatsoever. Whatever went off there was old, something that had been assembled long ago and then waited. 2 months later, a second short burst was pinned down inside the faint outskirts of a star-forming galaxy, well away from the regions where stars were actually being made, and in July a third was traced to another elliptical, this time with an X-ray, an optical, and the first radio afterglow ever recorded for a burst of this kind. The pattern held as the sample grew. Short bursts sit far from the centers of their host galaxies, at typical distances of 5 to 10,000 parsecs, and sometimes many times that, and somewhere between 30 and 45% of them occur at positions where deep imaging finds no detectable starlight at all. That displacement is itself a fingerprint. A binary formed from 2 supernovae has been kicked twice, and over the hundreds of millions of years it spends spiraling in, it drifts a long way from wherever it was born. In June of 2013, a short burst about 4 billion light-years away was followed with the Hubble Space Telescope, and about 9 days afterwards there was an excess of infrared light at its position that had no business being there. Too red for an afterglow, too faint to see in visible wavelengths at all, and in both brightness and color, a reasonable match to what had been predicted 15 years earlier. Two independent groups reported it within days of one another. It was the first sighting of anything resembling a kilonova, and it was, at best, a single unrepeated measurement of a faint red dot. By then, the idea had been in print for 24 years. Everything supporting it was circumstantial. The durations were right, the galaxies were the wrong kind for anything else. The offsets pointed at old wandering binaries, and one faint infrared excess had turned up where a kilonova should be. Nothing in that list amounted to seeing it happen. David Schramm, one of the four names on the 1989 paper, was killed in a plane crash in 1997. Bohdan Paczynski, who had been right about the fireball, right about the distances, and right about the kilonova, died of a brain tumor in 2007. There was only one way to convert the case into a fact. You would have to catch two neutron stars in the act of arriving, and since the collision announces itself in the ripples of space-time before it announces itself in light, that meant building something capable of hearing it first. The absurdity of the measurement is worth stating before anything else, because everything that follows depends on it having worked. A gravitational wave is a distortion in the geometry of space itself, and when one passes through a region, distances inside that region briefly change. Not the objects, the space between them. To catch one, you build an L, two arms 4 kilometers long, meeting at a right angle, with a laser at the corner. The beam is split, sent down both arms, bounced off mirrors at the far ends, and recombined. If the arms are exactly equal, the returning beams cancel one another out, and nothing reaches the detector. If a wave passes and stretches one arm while squeezing the other, they no longer cancel, and a flicker of light appears where there should be darkness. The change being looked for is about 1 part in 1,000 million. Across 4 kilometers, that works out to a shift in length a few hundred times smaller than the width of a single proton. The instruments have to hold that standard while sitting on a planet with traffic on it, and weather and earthquakes on the other side of the world, and they do it by being built in pairs 3,000 kilometers apart, so that anything appearing at only one site can be discarded. By the summer of 2017, there were 3 of them running, 2 in the United States and a European detector near Pisa that had joined the observing run on the 1st of August. It had been operating for just over a fortnight. At 41 minutes and 4 seconds past 12 Universal Time on the 17th of August, a signal entered the band. It began at around 30 cycles a second and climbed. Over the following 100 seconds, it rose through the whole sensitive range of the instruments, accelerating as it went, ending somewhere near 2,000 cycles a second before stopping abruptly. That rising sweep is the shape produced by 2 objects spiraling together. The tighter the orbit, the faster the circuit, the higher the note. 2 years earlier, the first such detection from a pair of black holes had lasted 1/5 of a second. This one sang for 1.5 minutes because neutron stars are light enough to spend a long time in the audible part of the descent. The signal was the loudest yet recorded, with a strength above the noise of 32, and the odds of the instruments producing something like it by chance came out at less than once in 80,000 years. The 2 objects weighed between about 9/10 and a little over 2 solar masses each, with a combined mass of 2 3/4, precisely the range in which the neutron stars catalogued in our own galaxy sit. Whatever had just happened had happened about 40 megaparsecs away, which is 130 million light-years. 1 3/4 seconds after the signal ended, a gamma-ray monitor in orbit triggered on a short burst lasting about 2 seconds from a region of sky consistent with the same source. A European gamma-ray observatory recorded it independently. A short gamma-ray burst had arrived within 2 seconds of the collision of 2 neutron stars, which was the thing that 4 physicists had written down in 1989 and nobody had been able to test. Then came the difficulty. Gravitational wave detectors are not telescopes and cannot point. They hear the whole sky at once, and direction has to be reconstructed from the tiny differences in when the signal arrives at each site. 2 detectors give a ring across the sky. 3 give a patch, and the patch in this case was helped enormously by the fact that the new European instrument had barely seen anything at all. Every detector has blind spots, directions in which it is nearly deaf, and a strong signal in 2 machines paired with near silence in the third is itself a powerful clue about where the source cannot be. The final region covered 28 square degrees. 28 square degrees is around 130 times the area of the full moon as you see it. For a large telescope, whose field of view is often a small fraction of 1 square degree, that is an impossible amount of sky to search in a night. So nobody searched the sky. Distance was known to within a few tens of megaparsecs, and within a volume that shallow, there is only a modest number of galaxies. Teams pulled up catalogues, made ranked lists of every galaxy lying inside the region at roughly the right distance. One group worked through 51 of them, and went down the list, photographing each one and comparing it against whatever archive images existed. It took the rest of the day. Somewhere in the middle of it, several thousand people across 6 continents were waiting on the outcome of what amounted to a filing exercise. Nothing was found for 10 hours and 54 minutes. Then, at 11:30 at night Universal Time, on a 1-meter telescope at Las Campanas in the Chilean Andes, a modest instrument by any modern standard, named after a woman who spent her career at the Mount Wilson Observatory, an image came down showing a point of light beside a galaxy where no point of light had been before. Over the following hour, several other teams working independently found the same dot. The galaxy is a lenticular one, elderly and largely finished with making stars, about 130 million light-years off. The new object sat a little to one side of its center, out in the quiet suburbs, exactly where a wandering old binary that had been drifting for a few 100 million years ought to end up. The light leaving that galaxy on the day of the collision set out early in the Cretaceous, while the continents were still coming apart, and it arrived on an ordinary Thursday in the middle of August, in a week you may well remember for entirely unrelated reasons, at a time of day when most of the people who eventually studied it were asleep. What followed was the largest coordinated observation in the history of the subject. Roughly 70 observatories on the ground and in orbit turned toward that one position, across radio, infrared, visible light, ultraviolet, X-rays and gamma rays, and kept looking for weeks. The paper describing the joint result carries several thousand authors, which is a reasonable proportion of everyone alive who works on this. 2 results came out of the timing alone, and both are worth more than they sound. The first concerns the 1 3/4 second gap. Gravity and light left the same place at very nearly the same moment and travelled 130 million years side by side, and they finished less than 2 seconds apart. Some part of that gap is not a race at all, but astrophysics. The jet takes a moment to form and to fight its way clear of the debris. So the true difference in speed is smaller still. Even taking the gap at face value, the speed of gravity and the speed of light agree to within about 1 part in 1,000 million. A whole family of alternative theories of gravity, several of which had been proposed to explain away dark energy, required the 2 to differ by more than that. Those theories did not survive the week. The second result is quieter and may prove more durable. The shape of a gravitational wave chirp encodes the distance to the source directly, without any of the calibration steps that ordinary astronomy has to climb through. No standard candles, no ladder of cross-checked rungs, each with its own uncertainties stacked on the one below. Combine that distance with how fast the host galaxy is receding, and the expansion rate of the universe falls out of a single event, measured a completely new way. The first answer came out at about 70 kilometers per second per megaparsec, with generous error bars, and it agreed with everything else. That number has since been refined, and the method now has a name of its own. It works on any merger with a visible counterpart, and there will be more of them. The signal itself was gone in 100 seconds. What had been left behind in that galaxy took much longer to fade, and while telescopes watched it over the following days, it did something that nothing in the catalogues had ever done. It changed color. On the first night, the new object beside that galaxy was blue and roughly as hot as the surface of the Sun, somewhere around 6,500 degrees. Within 3 days, it had fallen to about 3,500 and turned distinctly red. By the end of the week, most of its output had slid out of visible light altogether and into the infrared, and telescopes that had been watching in ordinary colors had to hand the job over to instruments that see heat. Nothing in the catalogues of transient objects behaves like that. Supernovae cool, but they cool slowly, and they do not run through the spectrum in a fortnight. Color in this context is not decoration. The light escaping an expanding cloud has to fight its way out through the material of the cloud itself, and how hard that fight is depends entirely on what the material is made of. Some elements are nearly transparent to visible light. Others are ferociously opaque, absorbing and re-emitting so persistently that photons take far longer to escape, emerge much later, and emerge much redder. So a color changing over days is a readout of composition, and what you are watching is the layers becoming visible in order. What the change was saying required a piece of nuclear physics that had been worked out on paper decades earlier, without anyone being able to point at a place where it happened. Stars build elements by fusion, but fusion stops at iron, because past that point, sticking nuclei together costs more energy than it releases. Everything heavier than iron on the periodic table, silver, tin, iodine, platinum, gold, lead, uranium, has to be made some other way, and the other way is neutron capture. A nucleus sitting in a bath of free neutrons will absorb one, and then another, growing heavier. The difficulty is that a nucleus with too many neutrons is unstable. Given time, one of those neutrons converts into a proton, and the nucleus becomes a different element, closer to stability, but no longer able to keep climbing. So it becomes a race. If neutrons arrive slowly, each one is absorbed, and the nucleus decays before the next arrives, and the process crawls up the chart of stable isotopes. That is what happens inside ordinary aging stars, and it produces about half of the heavy elements. But if neutrons arrive fast enough, a nucleus can swallow 10 or 20 or 30 of them before it has any chance to decay, and it is driven far out into a region of extreme neutron excess where no stable nucleus exists at all. Only when the supply runs out do those bloated nuclei collapse back towards stability in a cascade of decays, arriving at the heavy elements from above rather than climbing to them from below. That is the rapid process, and it requires neutron densities above about 100 million per cubic centimeter. Nowhere in the ordinary life of a star does anything approach that. A neutron star is made of very little else. When two of them are torn apart by each other's tides, a fraction of that material, perhaps a few percent of the Sun's mass, is flung out sideways rather than swallowed, at speeds up to a third of the speed of light. For a fraction of a second, that debris is the most neutron-rich matter in the universe, and it does in about 1 second what stellar fusion cannot do at all. The two-color behavior fits the geometry. The material squeezed out along the collision plane in the first milliseconds is the most neutron-rich, and it makes the heaviest products, including the lanthanides, the row of elements pulled out and set below the main body of the periodic table, which happen to be among the most opaque substances known. That component is slow, dense, and red. Material driven off the disk afterwards has been processed by neutrinos, is less neutron-rich, stops short of the lanthanides and is therefore relatively transparent, fast, and blue. Seeing blue first and red afterward is exactly what you get when a fast, clear shell outruns a slow, opaque one. Modeling the light curve gives the quantities. Something in the region of 6% of the Sun's mass was thrown clear and converted into heavy elements. Within that, the estimates work out at roughly 200 Earth masses of gold and something closer to 500 Earth masses of platinum. Two objects that had both already died, colliding once, manufactured several hundred planets worth of precious metal in about a second, and then scattered it into a galaxy where it will eventually find its way into gas clouds, and from there into stars, and from there into whatever forms around them. In 2019, that inference was converted into a direct measurement. Darragh Watson and his collaborators went back through the earliest spectra, taken at 1.5, 2.5 and 3.5 days, and found in them the distinctive signature of an expanding shell of strontium, an element with 38 protons sitting near the first peak of the rapid process distribution. It was the first time any freshly manufactured neutron capture element had been positively identified anywhere, not inferred from a light curve, named from a spectrum. Meanwhile, there was the problem of the burst itself, which had been oddly feeble. Short gamma-ray bursts are normally seen at distances of billions of light-years. This one went off 130 million light-years away, closer than any other on record, and it was faint. Orders of magnitude weaker than a typical short burst. Weak enough that had it occurred at ordinary distances, nothing would have registered. The answer came from radio telescopes on separate continents, combined so that the whole Earth acts as a single dish. Between 75 and 230 days after the merger, the radio source moved. The shift was under 3,000ths of an arcsecond, which is roughly the angular width of a couple of coins laid on the surface of the Moon, and translating that into a speed gave a figure of about 4 times the speed of light. Nothing was breaking any rules. Apparent superluminal motion is a projection effect, and it arises whenever something moving very close to light speed is aimed nearly, but not exactly, at the observer. The object is chasing the light it emitted a moment earlier. Each successive flash has a shorter distance left to travel before it reaches you, so the flashes arrive bunched together, compressed into a fraction of the time that actually elapsed. Divide the real sideways displacement by that compressed interval, and the answer comes out larger than the speed of light, without anything having exceeded it. Working backwards from the measurement gave the geometry. The jet had an opening angle under 5 degrees, and the Earth was sitting about 20 degrees off its axis. We had not been in the beam. What arrived was the ragged edge of a structured outflow, seen from the side, which is exactly why it was faint, and which was the first time anybody had measured the shape of one of these jets directly, rather than inferring it from a bend in a light curve. The second confirmed kilonova arrived in March of 2023, and it broke something. The burst lasted well over a minute, which by every convention makes it a long burst, and therefore a dying massive star. But no supernova appeared. Instead, mid-infrared observations with the James Webb Telescope at 29 and 61 days found a very red source, and at a wavelength of 2.15 microns, an emission line that has been interpreted as tellurium, element 52, sitting near the second peak of the rapid process distribution. It was not the only case. On the 11th of December 2021, a burst had gone off some 350 megaparsecs away with a duration of 50 seconds, unambiguously long by the 2-second convention, and the sort of event that ought to come with a hypernova attached. Deep imaging found no supernova at all, not at 10 days, not at 17. What it found instead was a kilonova. Whatever collided that day, it was not a single star coming apart. The line drawn in 1993 had always been a statistical convenience rather than a physical boundary, and these were the events that made the difference matter. Duration reflects how long the central engine runs, and a merger that leaves behind a magnetized remnant, or that involves a white dwarf rather than a second neutron star, can evidently keep an engine running for a minute. The classification has not been discarded because for the great majority of bursts, it still works. It has simply been demoted from a diagnosis to a strong hint. One further caution belongs here because it is the sort of thing that gets flattened in the retelling. Neutron star mergers are now a confirmed site of rapid process nucleosynthesis. Whether they are the main one is genuinely unsettled. Binaries take a long time to spiral in, anywhere from tens of millions to many billions of years, and that delay creates a problem in the oldest stars we can find. Extremely metal-poor stars, formed when the galaxy was very young, already contain europium, which is a rapid process element, and the models struggle to deliver it that early, using mergers alone. A study published in 2025 found that no single framework reproduces the europium patterns of the Milky Way and of its small companion galaxies at the same time. The leading alternative is a rare and violently magnetized kind of collapsing star, which would arrive on a much shorter clock. It may well be both. One event, caught once, settled a question that nuclear physics had been arguing about for 50 years, which raises the obvious follow-up, and it is not a comfortable one. How many of these had already happened, unrecorded, while nobody had anything pointed in the right direction? Somewhere above the atmosphere, a detector registers a rise in its count rate, and a clock starts. What happens over the following 90 seconds determines whether the event will be understood or merely counted. There is no possibility of a human being in that loop. By the time anybody has been telephoned, the gamma rays are finished. The afterglow has faded by a factor of several, and the position, if it was ever narrowed beyond a few degrees, has gone cold. The solution was built by a NASA engineer named Scott Barthelme, who in 1993 wrote software that watched the real-time telemetry coming down from the 8 detectors on the Compton Observatory and calculated a position automatically without waiting for anyone to look at it. The system distributed that position to whoever had asked to receive it. Over the following 18 months, the delivery methods multiplied in a way that now reads as a small history of the era. Telephone connections in July of 1993, electronic mail that December, direct machine-to-machine connections over the internet in January of 1994, and from September of that year, alphanumeric pages. For most of the 1990s, there were astronomers walking around with a pager on their belt that would go off at any hour of your day or theirs, because a star somewhere had ended. The first robotic telescope wired into the system joined in August 1993, 4 months after it began. The payoff arrived on the 23rd of January, 1999. A small automated instrument in New Mexico received an alert, slewed, and opened its shutter 22 seconds after the burst began, while the gamma rays were still arriving. On a 5-second exposure, it recorded an object of about 12th magnitude. 25 seconds later, it recorded the same object at 9th. For roughly a minute, something 9.5 billion light-years away was bright enough to be seen through a decent pair of binoculars by anyone who happened to be looking at the right patch of the constellation Boötes and knew what they were looking at, which was nobody. It was the first time any part of a gamma-ray burst had been observed at a wavelength other than gamma rays while it was still happening. Swift was built around that lesson. Launched on the 20th of November 2004, it carries a wide-field instrument that detects bursts and fixes their position to within a few arc minutes, and 2 narrow-field telescopes, one for X-rays, one for ultraviolet and visible light, that are useless unless they can be brought to bear immediately, so the spacecraft turns itself. It slews at up to a degree per second without instruction from the ground and typically has the X-ray telescope on target about 90 seconds after the trigger. The mission was named for the bird, which is a rare case of an acronym-hungry field, choosing a name that simply describes what the thing does. Between them, the standing instruments now produce a steady census. Swift alone has recorded something approaching 1,800 bursts across 2 decades, at roughly 90 a year, about a tenth of them short. The gamma-ray monitor on Fermi, which watches the whole unblocked sky at once, triggers around 240 times a year, of which 40 to 45 are short. Its higher energy telescope catches perhaps a tenth of those that fall inside its narrower field. Add in the other satellites and the total runs to a few hundred a year, which works out at very nearly 1 a day. While you have been listening to this, the odds are reasonable that one has arrived and been logged, and that a note about it has already gone out to several thousand subscribers. In 2019, the accessible energy range doubled. Ground-based telescopes that detect gamma rays indirectly by photographing the faint blue flash a high-energy photon makes when it slams into the upper atmosphere, recorded 2 bursts at energies above 100 billion electron volts. One of them, in January of that year, was caught at between 200 billion and 1 trillion electron volts, starting 62 seconds after the trigger and continuing for the better part of an hour. The explanation is a second act performed by the same electrons. Accelerated in the shock, they spiral through magnetic fields and radiate, producing the X-rays and visible light of the afterglow. Then some of them run into the light they have just made. Each such collision punts the photon's energy up by an enormous factor, producing a second component of the spectrum at energies the electrons could never have reached by spiraling alone. The afterglow, in effect, shines on itself, all of which is worth having for its own sake, but the deeper use of these events has nothing to do with what causes them. A burst afterglow is a lamp, an extremely bright one with a smooth, featureless spectrum, switched on for a few days in an arbitrary direction and at an arbitrary distance. Anything lying between it and the Earth leaves its fingerprints on the light. Gas clouds in the host galaxy, intervening galaxies, the thin material filling the space between galaxies. Each imprints its own absorption, and unlike a quasar, which sits in the same place forever and drowns out everything around it, a burst fades. Come back 3 months later and the lamp has been switched off, and the galaxy that contained it can be studied without the glare. That makes distance the most valuable property a burst can have. In April of 2009, one was recorded whose light had been stretched by a factor of more than 9, placing it about 630 million years after the beginning, a spectroscopic measurement confirmed by taking the light apart, and still the confirmed record. If the whole history of the universe were compressed into a single human life of 80 years, say yours, that star died before the 4th birthday. A second burst 3 weeks later was estimated to be further still, at a stretch factor above 10, but that estimate came from photometry rather than spectroscopy, from colors rather than from lines, and it has never been confirmed. The distinction matters and is worth keeping. One of those numbers is measured, the other is inferred. Bursts that distant may also be the only practical way to see the first generation of stars at all. Those objects, formed from gas containing nothing heavier than helium, are thought to have been extremely massive and extremely short-lived, and they are individually invisible to every telescope built or planned. But a massive, rapidly rotating metal-free star is very nearly the ideal collapser. If any of them ended that way, the beam is still traveling and something is now watching for it. 2 new instruments went up in 2024. One, launched in January, carries a wide-field X-ray telescope whose optics are copied from the eye of a lobster, a dense array of tiny square channels that focus by reflecting X-rays at grazing angles off their walls, which is the only way anybody has found to build an X-ray camera with a genuinely wide field. It sees roughly 3,500 square degrees in a single exposure, close to 1/10 of the entire sky, and it can cover almost all of the night sky in 3 orbits, which is about 5 hours. The second, a French-Chinese satellite launched in June and brought into full operation in April of 2025, had passed 100 bursts within its first 2 years and has already caught one whose light left when the universe was around 5% of its present age. None of this belongs to anyone. The alert network is open. The notices go out to whoever signs up for them, at no cost, in the same form and at the same moment, whether the recipient is a national observatory or you, with a telescope in a garden. The count now stands at several thousand recorded events, assembled by instruments built in 12 countries by people who mostly have not met, running continuously since the year the Berlin Wall was still standing, on the working assumption that if a star dies anywhere within reach, somebody should be pointed at it within the minute. Most of what the watch catches is unremarkable insofar as that word means anything in this context. Then, on an October morning in 2022, it caught something that the instruments had not been designed to survive. The first entry in the record is a mistake. When the alert went out, the position lay almost exactly along the plane of the Milky Way, the crowded band of the sky where our own galaxy's stars and gas pile up, and the signal was so strong that the automated classification took it for something local. It went into the catalogues as a new and unidentified hard X-ray source in our own galaxy, and it was given a name that describes a set of coordinates and nothing else. It kept that name for several hours. What unpicked it was cross-checking. The swift alert triggered an automatic search of the higher energy data from Fermi, which found a very bright signal at the same moment. That in turn prompted somebody to go back through the lower energy monitor's records, where the event turned out to be among the brightest things that instrument had ever registered. 3 teams compared positions, found them consistent, and concluded within the day that they were all looking at the same object, and that it was not in this galaxy at all. Then came the awkward business of measuring it. An instrument that has been overwhelmed does not simply record a large number. It records a wrong one because the electronics cannot distinguish 2 photons arriving almost together from a single more energetic one, and the error grows with the brightness. Reconstructing the true output meant working from the few detectors that had happened to be pointed at an unfavorable angle, from one Chinese monitor that had been designed with exactly this failure mode in mind and recorded the whole thing cleanly, and from the shape of the parts of the light curve that came before and after the peak. The final figure, around 70 times the previous record holder, is an inference from partial blindness, and it took months. The most beautiful measurement had nothing to do with the burst's own physics. Over the following weeks, X-ray telescopes photographing the position found rings. A series of them, perfectly concentric, centered on the source, expanding outward night after night. Each ring is a dust sheet lying between you and the source, inside our own galaxy. X-rays from the burst struck the dust, scattered through a small angle, and arrived slightly late, having taken a marginally longer path. Different dust clouds at different distances produce rings of different radii, growing at different rates. Around 20 were counted, from clouds 300 parsecs away out to nearly 19,000. For a few weeks, a flash from 1.9 billion light-years away was working as a searchlight for a cross-section of the Milky Way, and the layers of our own galaxy's dust were mapped by light that had left before there were animals on this planet. At the high end, something arrived that arguably should not have. An observatory on a Tibetan plateau, which detects gamma rays by photographing the shower of particles they produce in the upper atmosphere, recorded thousands of photons above 100 billion electron volts, and the most energetic of them came in at around 18 trillion. The problem is the journey. Space between galaxies is not empty. It is faintly lit by the accumulated starlight of every galaxy that has ever shone, and a sufficiently energetic gamma ray traveling through that glow will eventually collide with one of those ordinary photons and convert into a particle pair. It is the same trap that closed inside the source, operating over intergalactic distances. Standard models say a photon of 18 trillion electron volts crossing that distance should have been attenuated by a factor of somewhere between 1 million and 100 million. Several of them arrived anyway. Careful work has since shown that the observation can be squeezed inside the uncertainties of the starlight models at some strain. It has also produced a small library of papers proposing that the answer involves physics nobody has yet observed. A separate detector reported a shower consistent with a photon of 250 trillion electron volts, a claim that remains disputed and probably should. And then there is the reckoning, which is the part that matters most and gets quoted least. The energy figure attached to this burst assumes that it shone equally in every direction, and it did not. Modeling the afterglow across every wavelength gives a jet with an unusually narrow core, a half-opening angle of roughly 6/10 of a degree, carrying its energy mainly in magnetic fields rather than in matter, surrounded by a broader, shallower wing. A cone that narrow covers about 1 part in 18,000 of the sky, which means that when this thing went off, the probability that its beam happened to contain the Earth, and therefore you, was around 1 in 18,000, twice over. Correct for that, and the true energy released in gamma rays comes out somewhere between 1/10 and the whole of what the Sun will radiate across its entire existence, which is to say, entirely ordinary. It sits comfortably inside the range that every other long burst occupies. The brightest gamma-ray burst in recorded history was not a more powerful explosion than the others. It was an ordinary explosion, unusually close, fired through an unusually narrow aperture that happened to be aimed at this solar system. The supernova underneath it says the same thing, and this took longer to accept. There was a strong expectation that an event this extreme would come with a correspondingly extreme stellar explosion. Deep observations, including with the James Webb Telescope, found a supernova that is entirely unremarkable. No brighter, no more energetic, and no more chemically enriched than the ones accompanying perfectly average bursts. It is possible that the genuinely exceptional afterglow was simply drowning it out. It is also possible that the jet and the explosion are driven by different parts of the same collapse and are not obliged to scale together at all. Nobody has settled it. How often something like this arrives is also unsettled, and the number in circulation deserves less confidence than it usually receives. The standard estimate, obtained by extrapolating the distribution of ordinary burst brightnesses out to the extreme, is 1 every 10,000 years, which would make this the brightest burst since the last ice age. In 2024, Justin Finker and Sobur Razake argued that if bursts with jets this narrow constitute a separate population rather than the tail of the usual one, and if that population does not extend beyond a certain modest distance, the rate could be as frequent as 1 every 200 years. Distinguishing between those possibilities requires waiting to see whether another one turns up, which is a research program with an unfortunate timescale. The record for visibility belongs elsewhere. On the 19th of March 2008, at 12 minutes past 6 in the morning, a burst went off in the constellation Bertus, whose light had been traveling for about 7.5 billion years, more than half the age of the universe, and well over 1 billion years before the Sun and the Earth existed. For roughly 30 seconds, it reached an apparent brightness of magnitude 5.8, which is faint but genuinely within reach of the unaided human eye from a dark site. If you had been standing outside on a clear night, looking at that particular unremarkable patch of sky, you would have seen a star appear that had not been there, hold for half a minute, and fade. It remains the most distant object a human eye has ever registered without a telescope. For that half minute, the single dying star was putting out as much light as 10 million galaxies. The most recent surprise is barely a year old and has not settled into any category. On the 2nd of July, 2025, the Wide Field X-ray telescope on the Einstein probe caught a soft flare from a position in the plane of the sky where nothing was known to be. About a day later, not a second, not a minute, a day, Fermi recorded a gamma-ray burst from the same spot, then another, then a third. Hubble eventually placed the source in a dusty, massive galaxy whose light has been traveling for something close to 8 billion years, so it is unambiguously extragalactic, and the leading models involve a jet that is magnetically dominated and precessing, wobbling like a top as it fires. A burst that lasts a day and goes off repeatedly does not fit the collapsar picture, does not fit the merger picture, and did not exist in anybody's catalogue 2 years ago. All of which circles back to a question that has been sitting underneath this since 2 satellites over the Pacific recorded a flash they could not account for. These things happen. They happen somewhere within reach of our instruments roughly once a day. They release the energy of a star's entire lifetime through an opening narrower than the width of the full moon. And the only reason any of them are gentle is that they are far away. A gamma-ray burst does not set anything alight, and it is worth being exact about that before going further, because the mechanism is almost universally misdescribed. Gamma radiation does not reach the ground. It is stopped high up in the thin air of the stratosphere, and the energy it deposits there goes into breaking apart the molecules it encounters. Nitrogen in the atmosphere is ordinarily inert. 2 atoms bound together so tightly that almost nothing separates them, which is why the air is 4/5 nitrogen and nothing much happens. A sufficiently energetic photon separates them anyway. The freed atoms find oxygen and combine into nitric oxide, and nitric oxide is a catalyst for the destruction of ozone. The word catalyst is doing the important work in that sentence. A nitric oxide molecule meets an ozone molecule and takes an oxygen atom off it, becoming nitrogen dioxide and leaving behind ordinary oxygen. The nitrogen dioxide then meets a loose oxygen atom, gives up the atom it just acquired, and reverts to nitric oxide, unchanged and ready to do it again. Nothing is used up. A single molecule can run that loop thousands of times. It is the same catalytic arithmetic that made a modest quantity of industrial chlorine capable of opening a hole in the ozone layer over Antarctica, and it is the reason that a few seconds of radiation can have consequences lasting a decade. Modelling of a burst at the typical nearest distance over the last billion years gives global average ozone loss of up to 38%, with local depletion over some regions reaching 74%. Losses of at least 10% persist for 5 to 7 years. Full recovery takes 10 to 12. Along the way, the nitrogen dioxide produced in the process is brown and absorbs visible light, so the sky itself dims by a few percent, most strongly toward the poles, and the surface cools. What follows is not dramatic, and it is not fast. Ozone is what stops the shorter ultraviolet wavelengths of ordinary sunlight, and without enough of it, the sun that has been shining benignly for 4.5 billion years becomes, without changing in any way, a slow hazard. The damage rate to unprotected biological molecules rises by something like a factor of 16 above the annual average, and stays elevated for years. Anything living under a few meters of water is fine, because water absorbs ultraviolet efficiently. Anything living at the very top of the ocean is not, and the organisms at the top of the ocean are phytoplankton, which are the base of the marine food chain and are responsible for a substantial fraction of the oxygen in every breath. The mechanism of a mass extinction in this picture is not a death ray. It is a decade of sunburn applied to the bottom of the food web. For that to happen, the burst has to be close, and the threshold works out at roughly 2,000 parsecs, about 6,500 light years. That sounds enormous and is, by the standards of this documentary, negligible. It is around a quarter of the distance from here to the center of the galaxy, and it takes in a modest disk of the Milky Way's stars rather than the whole of it. Rate estimates suggest that over the last billion years, the expected distance to the nearest long burst is about that figure, which means there is a genuine possibility, somewhere in the region of a coin flip, that the Earth has been inside the dangerous radius at least once since complex life appeared. Short bursts, which are the more frequent kind in a galaxy like ours, turn out to be almost irrelevant to this. They release between 100 and 1,000 times less energy, and the corresponding danger radius collapses to something in the range of 13 to 40 light years, depending on which effect one worries about. Two neutron stars would essentially have to collide in the immediate stellar neighborhood. The nearest known binary of that kind is thousands of light years away and has hundreds of millions of years left to run. This is the point at which the late Ordovician usually gets mentioned, and it needs handling carefully. Around 445 million years ago, at the end of the Ordovician period, something removed roughly 60% of marine invertebrate genera in what remains one of the largest extinctions in the fossil record. In 2004, Adrian Mellott and Brian Thomas asked whether a gamma-ray burst could have started it, and the case they assembled is more interesting than it is usually given credit for. Extinction severity in that event correlates with how deep in the water column an organism lived and with how long it spent as free-floating larvae near the surface. Survivors are drawn disproportionately from deeper water and higher latitudes. Modeling the latitude dependence of ultraviolet damage against the observed pattern of losses, they found that only a burst arriving from over the South Pole produces the right shape. That is a real pattern, and it deserves to be taken seriously. It is also not proof, and the objections are equally real. Parts of the extinction appear to begin before the glaciation that a burst would supposedly have triggered. No climate simulation has yet demonstrated that the few percent of dimming involved is sufficient to start an ice age under late Ordovician conditions. And the ordinary terrestrial explanations, falling sea levels, glaciation, ocean chemistry, remain adequate on their own without requiring anything from outside the solar system. What exists is a hypothesis with a suggestive fingerprint attached. It is one candidate among several. It has been one candidate among several for 20 years, and anyone who tells you the Ordovician extinction was caused by a gamma-ray burst is reporting a possibility as though it were a finding. As for whether it could happen here, the honest answer is that the Milky Way appears to have stopped making the relevant kind of explosion some time ago. Long bursts require stars with a very low proportion of elements heavier than helium. The reason is mechanical. Heavy elements make a star's outer layers more opaque, which strengthens the wind it blows off itself, and a strong wind carries away angular momentum. A star that has been slowed down cannot form the disk the collapsar model needs. Where exactly the threshold sits is disputed. Published cutoffs range from about 1/6 of the Sun's heavy element content up to roughly 2/3. But the Milky Way sits above all of them. Our galaxy contains something like twice the heavy element content of the most enriched galaxy in which a long burst has ever been observed. Correcting the burst rate for that suppression cuts it by roughly a factor of 10, and the working conclusion is that this galaxy has been too chemically rich to produce long gamma-ray bursts for several billion years. Even setting that aside, the median jet is 7 degrees wide, so a burst that did occur somewhere in the Milky Way would still, with overwhelming probability, be pointing somewhere other than here, which leaves the one candidate anybody could name, and it has a satisfying ending. 8,000 light-years away in the direction of Sagittarius sits a Wolf-Rayet star in a binary system, wrapped in a spiral of dust laid down by the collision of the two stars' winds. Infrared imaging shows that spiral as a near-perfect pinwheel, and a pinwheel that looks circular is usually one being viewed straight down its rotation axis. Since the rotation axis is where the jet would go, and since a Wolf-Rayet star is exactly the sort of object that might eventually collapse, it spent 2 decades in the popular literature as the Death Star pointed at Earth. In September of 2024, Grant Hill at the Keck Observatory published the measurement that had never actually been made. Using 3 separate spectrographs, he tracked the 2 stars' motion toward and away from us over the course of their roughly 8-month orbit, which gives the tilt of the orbital plane directly rather than by inference from a picture. The orbit is inclined at least 30 to 40 degrees out of the plane of the sky, and possibly more. The dust spiral looks face-on. The orbit is not. Whatever eventually happens there, the poles are not aimed at us. It also left a genuine puzzle behind, which is why the dust should form a symmetric pinwheel around a system that is tilted, and papers on the question are still appearing. But the part that mattered outside astronomy has been settled, and settled in the ordinary way. Not by argument and not by reassurance, but by somebody taking a spectrum and measuring an angle that had been sitting there unmeasured for 20 years. So the sky above you tonight is not a loaded weapon. It is a place about which it is now possible to say something true and specific. And the deeper reason it is safe is not luck. This galaxy has grown too rich in heavy elements to make these events any longer. And it grew rich in heavy elements because generations of stars died in exactly this way and scattered what they made. The same process that would have been lethal at close range is the process that filled this galaxy with the material everything here is built out of, including the iron in your blood. Iron is where the ordinary account of matter runs out, and everything past it in the periodic table has to be explained some other way. That boundary is usually presented as a fact about stars. It is at least as much a fact about this planet and about the body listening to this, because a surprising amount of what is here sits on the far side of that line. Start with the ground. The Earth is losing heat from its interior at a rate of about 47 trillion watts, and roughly half of that is not left over from the planet's formation, but is being generated continuously right now by the decay of radioactive isotopes distributed through the mantle and the crust. 4 isotopes do most of that work, 2 of uranium, 1 of thorium, and 1 of potassium. The potassium was made in ordinary stars. The uranium and the thorium were not, and could not have been. There is no route to element 92 that goes gradually. Uranium exists only because somewhere, at some point, a great many neutrons arrived somewhere very fast. And that heat is not incidental. It drives convection in the mantle, and mantle convection drives the plates, and the plates drive mountain building and volcanism, and the slow subduction of carbonate rock that regulates how much carbon dioxide sits in the atmosphere over geological time. The thermostat that has kept this planet's surface temperature inside the range liquid water tolerates for most of 4 billion years is powered in significant part by the decay of atoms that were assembled in a fraction of a second during the destruction of something that had already died. The ground under this house is warm for the same reason there is gold in the ground at all. Then there is the smaller and stranger example. Iodine is not abundant, about a 0.010% of the crust, and it is made almost entirely by rapid neutron capture. It is also indispensable. The thyroid gland exists in order to concentrate iodine out of the bloodstream and build it into 2 hormones, which between them set the metabolic rate of essentially every tissue in the body and which are required for normal neurological development before birth. There is no substitute. No other element will do the job. Somewhere in your throat, right now, a gland the size of a small plum is holding onto a supply of an element that can only be manufactured in the destruction of a neutron star and using it to regulate how fast you are living. The most remarkable thing to come out of this in recent years is a date, and the method is worth describing because it is so unlikely that it works at all. Two of the isotopes made by rapid neutron capture, iodine-129 and curium-247, happen to have almost exactly the same half-life, a little under 16 million years. That coincidence is enormously useful. Both are radioactive and both decay away, so neither survives to the present day. But because they decay at the same rate, the ratio between them stays fixed while they are decaying, which means the ratio at the moment the solar system froze out of its parent cloud is preserved in the oldest meteorites, encoded in the abundances of the stable daughter products they left behind. And that ratio depends on how neutron-rich the material was in the event that made them, because a more neutron-rich source pushes further up the chart of elements and produces relatively more curium. Measure that ratio in meteorites, compare it against calculations of what different kinds of event would produce, and the result is a description of the last rapid process source to contribute material to the cloud that became the Sun. The answer, published in 2021, is that it was moderately neutron-rich, matching the kind of material that comes out of a neutron-star collision rather than the more extreme or more modest alternatives, and that it delivered its contribution somewhere in the region of 100 million years before the solar system formed. 100 million years is a long time and a short one. It means the material was already old and thoroughly stirred into the interstellar medium by the time the Sun condensed. It also means that whatever made the heaviest atoms in this room did so at a specific moment that can now be bracketed from a rock by counting the decay products of two isotopes that stopped existing 4.5 billion years ago. It should be said plainly at the end of all this that the picture is incomplete. Neutron-star mergers are confirmed as a site. Whether they are the principal one is unresolved. The europium in the oldest stars remains difficult to account for on merger timescales alone, and a rare class of violently magnetized collapsing star is still a serious competing contributor. The origin of the heaviest matter in a human body is a question with a partial answer, and the honest version of the story says so rather than rounding it up. What is not in doubt is where it ended up. Every gram of gold that human beings have ever dug out of this planet, all of it, across every mine and every riverbed and every civilization, going back to the first pieces hammered flat 6,000 or 7,000 years ago, amounts to a little over 200,000 tons. Melted together, it would form a cube about 22 meters on a side, which would fit comfortably inside a village church. All of it was manufactured somewhere else in less than a second before the Sun existed, and then spent several 100 million years drifting through a cloud of gas before that cloud collapsed, and some of it happened to end up in the crust of the third planet out. This galaxy has since moved past the phase that made all of it. The Milky Way is chemically rich now, and its richness is precisely the accumulated output of everything that has died in it. Every supernova, every collapsing star, every collision of two dead ones over roughly 13 billion years. That accumulation is the reason it is a comfortable place to live. It is also the reason it no longer makes long gamma-ray bursts, because the enrichment that fills a galaxy with useful material is the same enrichment that thickens stellar winds and slows massive stars down and prevents the whole mechanism from operating. The galaxy did not become safe by chance. It became safe by having already done the thing. Set against that, the human part of the story is very short. In 1973, when 3 physicists at Los Alamos published 4 pages describing 16 flashes, the entire body of knowledge on the subject was that they existed and were not local. There was no distance, no energy, no mechanism, no idea whether there were one kind or several, and no plausible physics that would allow the light to escape whatever was producing it. Everything in this documentary after that point was assembled in a single working lifetime out of nothing but arriving photons by people who could never go and look. And the instruments that started it were watching for something else entirely. The satellites over the Pacific in 1967 were built to detect a nuclear war, and their designers would have counted it a professional success if the machines had recorded nothing at all for their entire operational lives. In a sense, that is exactly what happened. The war they were built for did not come. What came instead, on the 2nd of July of that year, was a flash of gamma radiation from an object several billion light-years away, arriving at a set of detectors that were pointed in roughly the right direction by accident at almost the only moment in the history of this species when anything capable of noticing it existed. There is something worth staying with in the fact that none of this was written down anywhere. Matter keeps no record of its own history. A gold ring carries no trace of the collision that made it. The uranium warming the rock a few kilometers beneath this building does not remember the star it came out of. Every atom arrives anonymous, and there is nothing about holding one, or wearing one, or being partly built from one that reveals a single thing about where it has been. And yet the provenance is now known in outline, and it was worked out in under 60 years by people looking at faint dots through instruments they had built for other purposes. Nobody was told. There was no document to recover and no witness to interview. It was reconstructed. From the length of a flash, from the width of a line in a spectrum, from the color of a point of light beside an elderly galaxy, from an argument in an auditorium in Washington that neither side won. That is a strange thing for a species to have done, and it is stranger still that it was done almost entirely by people who will never see the objects they described in a galaxy that finished making them long before anyone was here to ask. We are living in the quiet afterwards. The violent era that assembled the material is over, at least in this neighborhood, and what remains is the settled house and the late arrivals in it, working out from the furniture what happened here before they came. Somewhere out there tonight, light is crossing the space between one galaxy and another from an event that ended before this planet had finished cooling. Some of it will reach the top of the atmosphere within the next few hours, and a detector will register it, and a short automated message will go out to a few thousand people, and the count will go up by one. Some of it will arrive in 10 million years at instruments that do not exist yet, built by people who have not been born. And a great deal of it will simply keep going, past everything, and never arrive anywhere at all. None of that needs anything from you tonight. The heavy elements are already made. They are already here, in the ground and the water and the salt, and in the small, warm machinery of a body lying still in a dark room. Whatever is happening out there at this moment, the light will take as long as it takes, and it is in no hurry. The galaxy is quieter than it was. It has done its loudest work already, and everything you are made of came out of that work, and it is finished, and it is safe now. Rest. There is nothing above you that needs your attention. Good night.